2002, in a delivery room in New York, a nurse drew a sample of umbilical cord blood from a newborn girl. The infant had just taken her first breath. Her mother had never worked in a chemical plant, never handled industrial solvents, never lived near a toxic waste site. When the laboratory ran the sample, they found polybrominated diphenyl ethers, not in some of the samples, in every sample. The chemicals had crossed the placenta and entered the fetal bloodstream before the child was born. The chemicals were not supposed to be there. They had been added to furniture foam to pass a 12-second flame test, a standard written in California in 1975 after a high-rise furniture mart fire killed 14 people. The test asked one question: if you hold a small flame to a block of foam for 12 seconds, does the foam self-extinguish? The chemical industry answered with bromine. The foam passed. The test did not ask what the bromine would do after the couch left the factory. It did not ask where the chemicals would go, how long they would last, or whether they would ever leave the body of a child. Now we descend. The surface noise of safety labels and compliance tags fades above us. The steel test chamber is still down there, sealed and quiet. So are the internal industry memos from 1983, filed in cabinets and never released. So is the dust in a nursery in Oakland, the sediment at the bottom of Lake Michigan, the breast milk of nursing mothers whose chemical inventory doubled every 5 years. The hatch seals. The pressure builds. The beam finds the first file. There is a room where the furniture burns. Not the furniture in the showroom, not the furniture in the living room. The furniture in the test chamber, a steel box the size of a small closet, lined with ceramic wool, ventilated by a hood that pulls smoke upward and away. Inside, a block of polyurethane foam sits on a metal grating, cut to a precise rectangle, conditioned to a specific humidity, instrumented with thermocouples. A technician in a flame-resistant coat opens the door, reaches in with a laboratory burner, and applies a small flame to the foam for exactly 12 seconds. Then he removes the flame and watches. The room smells like a television that has been left on too long, acrid, synthetic. The odor of melted plastic and scorched chemical additives. The foam blackens. It chars. In many cases, before the standard, it continued to burn until the block was consumed, collapsing into a puddle of molten polymer, releasing dense black smoke. In the years after the standard changed, the foam does something else. The flame touches it, spreads briefly across the surface, and then, as if the foam has decided not to participate, goes out. The charred surface smolders for a moment and stops. The foam has passed. This moment, repeated thousands of times in testing laboratories across the United States, is the origin of a chemical transformation that would eventually reach every American home. The test was called the open flame test, and it was the centerpiece of Technical Bulletin 117, the flammability standard adopted by the state of California in 1975. The standard was born from a fire, a real one, not a test, and the fire was one of the worst in the state's history. On the morning of August 5, 1975, a fire broke out on the 7th floor of the Los Angeles Furniture Mart, a 12-story building in the city's downtown wholesale district. The building was filled with upholstered furniture, foam cushions, fabric displays, and the ordinary materials of the home furnishings trade. The fire spread through the upholstery as if the furniture had been designed to carry flame from one room to the next. By the time it was over, 14 people were dead and dozens more injured. The state fire marshal's investigation concluded that the foam and fabric in the building's furniture had accelerated the blaze to a speed that made escape impossible for those trapped on the upper floors. California responded with Technical Bulletin 117, the most aggressive residential furniture flammability standard in the nation. The standard's logic was direct. If the filling materials in upholstered furniture could resist a small open flame, fires like the one at the Furniture Mart would be slower to grow, giving occupants more time to escape. The test was simple. Apply a flame to the foam for 12 seconds. If the foam caught fire and continued to burn, it failed. If it self-extinguished, it passed. The question the test asked was clear and narrow. Does this material sustain combustion under these specific conditions? The answer the foam industry found was a family of chemicals called polybrominated diphenyl ethers, PBDEs. These compounds, added to polyurethane foam at concentrations between 5 and 30% by weight, made the foam flame resistant. When heated, the bromine atoms in the molecule released free radicals that interrupted the chemical chain reaction of combustion in the gas phase above the burning material. The foam might still char. It might still decompose, but it would not sustain a flame. The test chamber recorded a pass. The standard was satisfied. The furniture could be sold. But the test measured only one thing. It measured whether a piece of foam, exposed to a small flame for 12 seconds, would continue to burn. It did not measure whether the chemicals added to that foam would, over the years of ordinary use, leave the foam and enter the air, the dust, the bodies of the people who lived with it. The test was silent on the question of chronic exposure. It asked nothing about what happens when a chemical designed to survive fire enters a body designed to survive the world. The flame extinguished. The foam passed. The record of the test shows only the pass. The strange part was not that the chemicals worked. The strange part was that the test asked so little of them, and the standard asked so little of the test, and the whole arrangement, the flame, the foam, the bromine, the 12-second stopwatch, became a kind of covenant between safety and ignorance. The covenant said, if the foam does not burn for more than 12 seconds, the chemicals in the foam are safe enough. The covenant did not say this in writing. It said it in procedure. The procedure became the proof. What happened next was not a secret exactly. The chemicals that made the foam flame resistant were not chemically bonded to the polyurethane matrix. They were mixed in, physically dispersed, a guest that had been invited to stay but never asked to sign a lease. Over time, through the ordinary friction of sitting and standing, through the slow mechanical degradation of the foam, through the invisible abrasion of fabric against cushion, the chemicals migrated out. They adhered to particles of household dust. They rose into the air when the dust was disturbed. They settled back onto carpets, onto television screens, onto the surfaces of toys and books, and the hands of children who crawled across the floor. The couch was passing the test, but the test was not the only thing happening in the room. The flame extinguished. The foam passed. The chemicals that saved that foam from burning had already begun the slow, invisible process of leaving the furniture and entering the air, the dust, and the bodies of everyone who lived with it. This was not a failure of the test. This was a failure of the question the test had been designed to ask. The test asked whether the foam would burn. It did not ask whether the foam would release. It did not ask whether the chemical that survived the flame would survive the body. It did not ask whether a 12-second test could predict the behavior of a molecule over a decade. And so the test chamber became a point of departure. The foam passed through it, acquired its certification, and entered the supply chain. From the supply chain, it entered the factory floor, where workers cut and shaped it, breathing the yellow dust that settled on every surface. From the factory, it entered the furniture showroom, where salespeople showed it to customers who ran their hands over the fabric and asked about durability and stain resistance, and never once about flame retardants. And from the showroom, it entered the home, where it became the couch, the nursery glider, the car seat, the mattress pad, the ordinary object that someone sat on every evening for years, unaware that the foam was slowly exhaling its chemical contents into the room. A couch is not just a couch. A couch is a reservoir. It holds the dust of the room, the shed skin cells of the people who sit on it, the microscopic debris of everyday life. And it holds, in its polyurethane structure, the bromine atoms that were added to pass a test in a steel chamber in 1976. Those atoms do not stay put. They move. They cross the air gap between the cushion and the floor. They enter the body through the lungs and the gut, through the hand that touches the dust and then touches the mouth. They cross the placenta. They enter breast milk. They become part of the chemical composition of the people who never knew they were being exposed to anything at all. The test chamber never measured any of this. It could not. Its purpose was to answer a single question under controlled conditions, and it answered that question faithfully year after year until the answer became a standard, and the standard became an industry. And the industry became a chemical legacy that would persist in the bodies of Americans long after the foam itself had been thrown away. The flame extinguished in 12 seconds. The consequences would take decades to become visible. What was missing from the test chamber was not the equipment. The equipment was adequate. The thermocouples recorded the temperature. The stopwatch measured the time. The hood vented the smoke. What was missing was the other chamber, the one on the other side of the test, the one where the foam went after it passed and before it burned. That chamber was the living room. And the living room had no instrumentation, no stopwatch, no protocol for measuring what accumulated there. The living room was running its own experiment, but nobody was recording the data. The test chamber still exists. It is still used, though the standard has changed, and the open flame has been replaced by a smoldering cigarette, and the foam no longer needs to carry the weight of bromine to pass. But the couches that were made under the old standard are still here. They are in basements and attics and secondhand stores. They are in landfills where they release their bromine into the leachate and the groundwater. They are in the dust of homes that have been vacuumed 1,000 times since the standard changed. Because the chemicals that left the foam in 1998 are still present in the dust of 2025, having settled into the carpet padding, having adhered to the subfloor, having become part of the permanent chemical background of the indoor environment. A test is a kind of promise. It promises that the thing being tested has been asked the right questions. The open flame test promised that the foam was safe from fire. It did not promise that the foam was safe. The difference between those two promises is the difference between the test chamber and the living room, and the living room was never the one being measured. The flame extinguished. The foam passed. The technician noted the result on a clipboard and moved on to the next sample. And in a living room somewhere in California, a couch that had passed the test was beginning its long, invisible migration from furniture to dust to body. The test was over. The story was not. The bandsaw bit into the foam block with a sound like tearing bread. It was 1976, and on the floor of a plant in El Dorado, Arkansas, the air carried a particular kind of dust, yellow, fine, settling on the steel housings of the cutting machines, on the shoulders of the workers, on the lenses of their safety glasses. The foam being cut was polyurethane, but it was not just polyurethane. It had been infused with a chemical mixture that would come to be known by its trade designation, diphenyl. The workers did not call it that. They called it the smell. The smell was the thing everyone remembered. It was sharp and synthetic, a kind of halogen tang that stuck to the back of the throat, like a swimming pool with no water, like the moment a television set overheats and you know something inside has begun to change irreversibly. The foam blocks came out of the curing oven still warm, and the bandsaws reduced them to slabs, cushions, bolsters, and the dust rose. It rose and it settled, and the workers went home with it on their clothes, in their hair, in the creases of their work boots. The dust was not just on them, but that realization was still decades away. This is a story about a molecule that would not die. Not in the foam, not in the air, not in the body. It is a story about the strange career of a chemical that was designed to save lives, and did, or at least, it passed the test that was supposed to prove it could. The chemicals in that Arkansas dust belonged to a family called polybrominated diphenyl ethers, PBDEs, in the compression of regulatory shorthand. They are halogenated flame retardants, and their mechanism is, in its own terms, elegant. When polyurethane foam treated with PBDEs is exposed to heat, the bromine atoms bonded to the ether rings begin to move. At a threshold temperature, they release free radicals, highly reactive bromine species that enter the gas phase above the material. Combustion, at its chemical root, is a chain reaction, free radicals generated by the burning polymer attack neighboring molecules, breaking them down into more radicals, which attack more molecules in a self-sustaining cascade. The bromine atoms interrupt this cascade. They scavenge the radicals before they can propagate, terminating the chain. The foam may still blacken and char. It may still deform, but it will not sustain a flame. That was the test. A 12-second exposure to an open flame. The foam had to self-extinguish. PBDEs made sure it did. But the same chemical feature that gave PBDEs their protective power, their thermal stability, their refusal to break apart under the conditions that would destroy lesser compounds, also gave them a more troubling career outside the test chamber. A molecule that will not burn will also not easily degrade. It will not yield to sunlight or water or the slow enzymatic gnawing of soil bacteria. It will persist. And persistence, in the language of environmental chemistry, is not a metaphor. It is a physical property with consequences. To understand what happened next, you have to understand what these molecules actually were. The commercial product, diphenyl, was not a single compound. It was a mixture, a blend of congeners, molecules with the same basic architecture but different numbers and arrangements of bromine atoms bound to the diphenyl ether backbone. There were tetrabrominated congeners with 4 bromines, penta- with 5, hexa- with 6. Each had a slightly different shape, a slightly different polarity, a slightly different affinity for fat versus water. Each would go on to have a slightly different career in the environment and in the bodies of the people who absorbed them. The diphenyl ether backbone itself, two benzene rings joined by an oxygen atom, was not new to industrial chemistry. It was structurally familiar. It was, in fact, almost identical to the backbone of another class of compounds, polychlorinated biphenyls, or PCBs. PCBs had been the great industrial triumph of the mid-20th century, stable, non-flammable, electrically insulating, ideal for transformers and capacitors and hydraulic systems, and they had become the great industrial scandal of the 1970s. By the time the workers in El Dorado were cutting treated foam, PCBs had already been banned in the United States. The ban had come in 1979 under the Toxic Substances Control Act, after nearly a decade of mounting evidence that PCBs accumulated in the tissues of wildlife, persisted in sediments, and caused a range of toxic effects in laboratory animals and exposed humans. The molecular resemblance between PCBs and PBDEs was noted in the scientific literature. It was not a secret. It was simply not, in any regulatory sense, acted upon. The logic of substitution is one of the recurring patterns in industrial chemistry. When one compound becomes politically or legally untenable, a structurally similar compound is introduced to take its place. The new compound is not identical to the old one. A chlorine atom replaced by a bromine, a side chain modified, a functional group shifted, but it is, in the ways that matter for persistence and bioaccumulation, the same kind of creature, the same broad shape, the same tendency to dissolve in fat rather than water, the same resistance to metabolic breakdown, the same long half-life in the tissues of any organism unlucky enough to ingest it. And the evidence that PBDEs behave this way was not absent in 1976. It was simply quiet and kept in places where the public could not see it. The company that produced DE-71 Great Lakes Chemical Corporation, based in West Lafayette, Indiana, was the world's largest manufacturer of brominated flame retardants. It had conducted its own toxicological studies. The studies were not published in peer-reviewed journals. They were kept in company files, submitted to regulators when required, and summarized in ways that emphasized the product's safety. What those files showed, what would only become public decades later in the slow unsealing of corporate archives, was that PBDEs accumulated in the liver tissue of laboratory animals within days of exposure. The liver is the body's central processing plant for foreign compounds, and it is often the first organ to show the signature of a chemical that will not leave. The workers in El Dorado did not know this. They knew the smell, and the dust, and the way the dust coated the inside of their noses and made them cough in the parking lot at the end of a shift. They knew that the foam they were cutting was going into furniture, couches, armchairs, crib mattresses, the padded seats of station wagons. They knew that the furniture was being sold to families across the United States, families who had no idea that their new sofa contained, by weight, anywhere from 5 to 30% flame retardant chemicals. They knew none of the molecular details. They knew the work. And the work was this. Polyurethane foam is a polymer, a network of long chains cross-linked into a sponge-like matrix. The flame retardant is mixed into the liquid precursors before the foam rises. It is not chemically bonded to the polymer. It is a guest in the structure, not a part of the structure. It sits in the foam the way water sits in a sponge, physically dispersed, held in place by the geometry of the material, but free to move. Over time, it migrates, it escapes the foam and enters the air, It settles onto surfaces. It becomes part of the dust. The dust in a living room is not inert. It is a suspension of materials, skin cells, fibers from clothing, pollen, soil tracked in from outside, and, increasingly in the late 20th century, the chemical residues of modern life. Phthalates from vinyl flooring, pesticides from gardens, and PBDEs from furniture. The dust is stirred by movement, a child crawling, a vacuum cleaner, the closing of a door, and then it settles again, a fine film on every horizontal surface. It enters the body through ingestion primarily. A hand touches the floor, the hand goes to the mouth, the dust is swallowed. In a toddler who spends hours on the carpet and explores the world with the wet membranes of lips and tongue, the dose is highest. The factory in El Dorado was the point of origin, but it was not the only point of exposure. The foam left the factory and went into homes. The dust in those homes became the primary vector for human contact with PBDEs. And the chemicals, once inside the body, behaved exactly as their PCB-like structure predicted. They moved into fatty tissues. They crossed cell membranes. They resisted the liver's attempts to break them down into water-soluble forms that could be excreted. They accumulated. The half-life of the most common PBDE congenitor in human blood, a compound called BDE47, with 4 bromine atoms arranged on the diphenyl ether backbone, is approximately 2.9 years. That number deserves a moment of attention. If a person is exposed to a single dose of BDE47, it will take nearly 3 years for half of that dose to be cleared from the bloodstream. For the more heavily brominated congeners, BD99, BDE153, the half-life can stretch to a decade or more, and exposure was not a single dose. It was continuous. Every day, from the couch, from the mattress, from the dust on the television screen, a fresh increment of the chemical entered the body. The blood levels rose. They rose in the workers in El Dorado who breathed the dust directly. They rose in the families who bought the furniture. They rose in the infants who had never been inside the factory, who had never even seen the state of Arkansas. The nursing mothers were the canaries, though no one knew it yet. In the late 1990s, Swedish scientists began analyzing breast milk samples for persistent organic pollutants. They were looking for PCBs mostly, and for dioxins. What they found, in addition to those expected compounds, was a new signature, a cluster of brominated molecules that had not been prominent in samples from the 1970s. The levels were doubling every 5 years. The trend line pointed upward, steep and unbroken, and the source was not industrial contamination of waterways or food chains. The source was indoors. The source was the dust. The women who nursed their children in the 1980s and 1990s were transferring, through the most intimate medium the body can produce, a chemical that had been added to their couches to pass a 12-second flame test. Their own bodies had become reservoirs, and the reservoirs were filling. The foam that would not burn had become the molecule that would not leave. The paradox sits at the center of the story like a stone in a piece of fruit. The property that made PBDEs valuable, their thermal stability, their refusal to disintegrate under the conditions of a fire, is exactly the property that made them permanent residents of the global environment. A molecule that will not participate in combustion will also not participate in photolysis or hydrolysis or microbial degradation. It is stable. It is inert. It is, in the most literal sense, unkillable. And that stability is not a design flaw. It is the design. The factory floor in 1976 was full of a substance that was already beginning its migration. The yellow dust that settled on the bandsaws and the safety glasses and the shoulders of the workers was not the end of a process. It was the beginning of a distribution. The foam blocks were loaded onto trucks. The trucks drove to furniture manufacturers. The furniture was shipped to showrooms. The showrooms sold it to families. And in every living room, in every nursery, in every dust-filled corner of every American home, the molecules continued their quiet work of leaving the foam and entering the air and finding their way, eventually, into the warm and welcoming medium of human tissue. The workers in El Dorado went home with the dust on their clothes. But the dust was not just on their clothes. It was in their lungs, their blood, their livers, their fat. And years later, when the first studies of PBDEs in human breast milk were published, the chemicals were found in the milk of nursing mothers who had never set foot inside a factory, who had never heard of El Dorado, who had simply bought a couch and lived with it and fed their children in the room where the couch sat. The foam that would not die had found its way into the most protected spaces the human body can offer, and it was only beginning. The foam samples moved from hand to hand under the fluorescent light of the convention hall, soft rectangles of pale yellow padding, each one carrying a promise that no one in the room had yet learned to distrust. It was 1981. The Furniture Manufacturers Association had taken over a wing of the Dallas Market Center, and the corridor smelled of new upholstery, coffee from stainless steel urns, and the faint sharp tang of bromine, a chlorine cousin with a heavier atomic signature. Drifting off the display boards where chemical salesmen had pinned their brochures like specimens. The brochure showed molecular diagrams, hexagons and bromine atoms rendered in crisp black ink, with captions that explained how these compounds interrupted combustion at the gas phase level. They did not explain what happened in the body when the same molecules migrated off the foam and settled into the dust of a living room. A salesman from Great Lakes Chemical Corporation, the company that would come to dominate the American market for flame-retardant chemicals, handed a brochure to a furniture executive and said something that had become standard in the industry: tested, proven, safe. The executive tucked the brochure into his jacket pocket. He would later specify that his company's new line of sofas should meet the California standard at the lowest possible cost. The chemical pathway was the cheapest. The chemical pathway became the default. The standard in question was Technical Bulletin 117, California's open flame test for residential furniture filling materials. It had been adopted in 1975 after a fire at a Los Angeles furniture mart killed 14 people, and it required that a block of polyurethane foam, when exposed to a 12-second open flame, self-extinguish within a specified time. Without chemical additives, the foam would catch and burn like solidified gasoline. With additives, it passed. The flame went out. The test did not ask what the additives would do after the couch left the factory. It did not ask where they would go, how long they would last, or whether they would ever leave the body of a child who crawled across the carpet. The test asked one question: does the foam resist a small flame for 12 seconds? The industry answered with chemistry. Great Lakes Chemical Corporation was headquartered in West Lafayette, Indiana, but its roots reached deeper into the brine wells of Arkansas, where bromine-rich waters had been tapped for decades, and into the laboratories where halogenated compounds were synthesized, tested, and brought to market. By 1981, the company was the world's largest producer of bromine-based chemicals, and its product line included the mixture known as D7-1, a blend of tetra-, penta- and hexabrominated diphenyl ethers. These were the polybrominated diphenyl ethers, or PBDEs, that would eventually saturate the indoor environment of the developed world. They were effective. They were cheap. They were about to become ubiquitous. The strange part was not that the chemicals worked. It was that nobody in the regulatory apparatus had asked the second question: what happens when a molecule designed to resist fire enters a system that has no fire to resist? The answer was already forming in the livers of laboratory rats, in the filing cabinets of the manufacturer, in the memos that would not see daylight for another 2 decades. The tobacco industry understood the value of a second question, but it applied that understanding in a different direction. For years, the cigarette manufacturers had battled against flammability standards for furniture. Their fear was obvious and well documented. If furniture had to be fire-resistant, then the pressure would logically fall on the ignition source, the cigarette. Fire-safe cigarettes, which self-extinguish when not actively puffed, had been technologically feasible since the 1930s. The tobacco industry had consistently opposed mandates for them, arguing that the solution to furniture fires was not a safer cigarette but a more fire-resistant couch. This position had been difficult to maintain while furniture burned easily. The chemical flame retardants offered a way out. If every couch in America could be treated with a compound that stopped a flame, the cigarette could remain unchanged. The burden would shift from the product that caused the fire to the product that received it. The 1981 revision of Technical Bulletin 117 was the moment that shift became permanent. The revised standard explicitly allowed the use of flame-retardant chemicals to achieve compliance. It did not require manufacturers to use barrier fabrics, inherently flame-resistant fibers, or design changes that might have reduced ignition risk without chemical additives. The chemical pathway was not just one option among many. It was the path of least resistance, the one that required no redesign, no new materials, no rethinking of the cigarette's role. The tobacco industry, which had spent decades fighting fire safety regulations, became one of the strongest advocates for chemical flame retardants. The couch would take the blame for the cigarette. This was not a conspiracy of villains meeting in a smoke-filled room. It was something more ordinary and more durable, an alignment of incentives. The chemical companies wanted to sell bromine. The furniture manufacturers wanted to meet the standard cheaply. The tobacco companies wanted to keep selling cigarettes as they were. The regulators wanted a solution that could be written into a technical bulletin and enforced with a flame. The legislature wanted to prevent another Furniture Mart fire. Everyone got what they wanted, except the people who would later sit on those couches, breathe the dust from those couches, and carry the chemicals from those couches in their blood for years after the furniture had been thrown away. The 1981 trade show in Dallas was the victory lap for this alignment. The foam samples circulated like party favors, each one a demonstration that the flame test could be passed, that the standard could be met, that safety could be added by the pound. The chemicals salesmen wore suits and carried attaché cases with technical data sheets printed on heavy stock. They talked about free radicals and flame inhibition, about the elegance of bromine chemistry, about the testing that had been conducted to confirm the safety of their products. They did not talk about what the testing had found. In the archives of Great Lakes Chemical Corporation, in a set of manila folders that would later be discovered by investigative journalists and subpoenaed by congressional committees, there was an internal study from the early 1980s. The study had exposed laboratory animals to PBDEs and examined their tissues after a short period. The results were clear. The chemicals accumulated in the liver within days of exposure. They did not pass through the body and disappear. They lodged in the tissue, concentrated in the organ responsible for filtering toxins, and remained there. The implications were not subtle. A chemical that bioaccumulates in the liver of a rat is likely to bioaccumulate in the liver of a human. A chemical that persists in tissue is a chemical that will accumulate over time, with every day of exposure adding to the body's burden. The study was not submitted to the Environmental Protection Agency. It was not shared with the California Bureau of Home Furnishings. It was not mentioned in the brochures handed out at the Dallas trade show. It was placed in a file, marked confidential, and stored in a cabinet. The record shows a chemical that passed a 12-second flame test. The margin shows a study that was never released. The strange part was not that the company had conducted the study. It was that the company had conducted the study and then behaved as though the study did not exist. The logic of the flame retardant industry in those years was not dissimilar from the logic of the tobacco industry it had allied with. The product was legal. The standard was mandatory. The testing, such as it was, had been performed. The long-term consequences, if they existed, were uncertain and would take years to materialize. If the chemicals turned out to be harmful, that was a problem for the future, and the future had no seat at the table in 1981. The future was not a regulator. The future was not a customer. The future was an abstraction, a hypothetical child crawling on a hypothetical carpet, a hypothetical liver accumulating a hypothetical dose. But the dose was not hypothetical. Even in 1981, the chemistry of these compounds made it inevitable that they would escape the foam. PBDEs are not chemically bonded to the polyurethane matrix. They are mixed in as additives, dissolved or dispersed in the material. Over time, they migrate to the surface, enter the air, and settle into dust. This migration is not a failure of the product. It is a consequence of the same physical chemistry that makes the molecules effective. A molecule that is stable enough to interrupt combustion is stable enough to survive in a living room for the lifetime of the furniture. A molecule that is not chemically bound will eventually leave. This was not a secret. It was basic materials science. It was simply never discussed in the trade show brochures. The 1981 revision of TB 117 was written in the language of technical specification, but it functioned as a treaty. The parties were the state of California, the furniture industry, the chemical industry, and the tobacco industry. The terms were simple. The furniture industry would add flame retardants to its foam. The chemical industry would supply the compounds. The tobacco industry would continue to sell cigarettes without fire-safe modifications. The state would enforce the standard and claim credit for fire safety. No one signed a document in a single room, but the signatures were there nonetheless. In the regulatory text, in the purchase orders, in the product labels, in the blood of the first human subjects whose cord blood would be sampled 17 years later. The treaty had a cost. The cost was not paid by the signatories. It was paid by the children who would be born in the 1980s and 1990s, whose mothers had lived with PBDE-treated furniture throughout their pregnancies, whose cord blood would eventually be tested and found to contain the same chemicals that had been accumulating in the livers of those laboratory rats. The chemicals migrated from couch to dust, from dust to hand, from hand to mouth, from gut to blood, and from blood across the placental barrier into the developing brain of a fetus. The pathway was long and invisible, but it was uninterrupted. The foam was fire-resistant. The child was not. The chemical industry's internal study of liver accumulation was not an isolated incident. It was part of a pattern that would only become visible decades later, when the internal documents surfaced in litigation and congressional hearings. The pattern was this: the industry tested its products, found evidence of persistence and bioaccumulation, and then filed the results away. When regulators asked for data, the industry provided summaries that emphasized the benefits of flame retardancy and minimized the toxicological signals. When independent scientists began publishing studies in the 1990s showing that PBDEs were contaminating human breast milk, the industry responded with public statements about the lack of definitive proof of harm. The definition of definitive was elastic. The burden of proof was placed on the bodies that were already carrying the chemicals. The 1981 trade show in Dallas ended. The foam samples were packed into boxes and shipped back to laboratories. The brochures were filed or discarded. The furniture executives returned to their factories and began specifying PBDE-treated foam in their new product lines. Within 5 years, the majority of upholstered furniture sold in the United States contained these chemicals. A couch bought in 1982 would still be shedding flame retardant into a living room in 1992, 2002, 2012, and beyond, long after the chemical had been phased out, long after the standard had changed, long after the original owner had died or moved or thrown the couch away. The dust would persist. The dust does not forget what it has absorbed. There is a photograph from that era that surfaced years later, not in a corporate archive, but in an industry publication. A chemist at Great Lakes Chemical holding up a flask of brominated compound, the liquid catching the light, his expression one of professional satisfaction. The photograph is undated, but probably from the late 1970s or early 1980s. It does not look sinister. It looks like a photograph of a man who has done his job well, who has made a product that solves a problem, who believes in the value of applied chemistry. The problem with the photograph is not what it shows, but what it does not show. The liver tissues enlarging under a microscope in a study that will not be released. The breast milk of a Swedish mother accumulating a chemical she has never heard of. The cord blood of a newborn in New York carrying a molecular signature that originated in a factory in Arkansas. The cost was already embedded in the chemistry. The flame was already out. The residue was already settling. The good neighbor of the story's title is not a person. It is a role that the chemical industry learned to play, that the tobacco industry had perfected, that any institution can assume when the consequences of its products are distant, slow, and distributed across millions of ordinary lives. The good neighbor is cooperative, responsive, reasonable. It participates in regulatory proceedings. It funds research. It offers solutions. It does not acknowledge harm until harm is impossible to deny, and even then, it frames the acknowledgement as a voluntary gesture of corporate responsibility, a phase-out, a reformulation, a new product with a new name, and a new set of unknowns. The good neighbor does not apologize, because apology implies liability, and liability implies a debt that the neighbor has no intention of paying. The ledger remains closed. The cabinet remains locked. The confidential study of liver accumulation was not a secret in the sense of a hidden document that no one could find. It was a secret in the sense of a document that was not meant to circulate beyond the people who already understood what it meant. The people who understood were the company toxicologists, the product managers, the regulatory affairs specialists. They knew that the chemicals were accumulating in tissue. They knew that the accumulation was measurable within days. They knew that the exposure pathway for humans, indoor dust, would deliver a chronic low dose over years. They did not need a longitudinal epidemiological study to understand that this was a problem. They needed only the data they already had and the integrity to act on it. They did not act. The filing cabinet closed. The 1981 revision of TB 117 remained in effect until 2013. For 32 years, the chemical pathway was the default pathway. During those 3 decades, an entire generation of Americans was born, grew up, and had children of their own while living in homes saturated with flame-retardant dust. The children played on treated carpet padding. They slept on treated crib mattresses. They watched television sets whose plastic housings contained additional flame retardants. They put their hands in their mouths. The dose accumulated. The body kept its own record, encoded not in paper, but in adipose tissue, in serum lipids, in the thyroid hormones that regulated brain development and metabolism. The record was chemical, invisible, and inescapable. The trade show in 1981 was not the beginning of the story. The beginning had come earlier, in the brine wells and the test chambers, and the legislative hearings that followed the Los Angeles fire. But the trade show was the moment when the story became operational, when the promises were distributed, and the brochures were pocketed, and the foam samples were carried home to become the cushions of a nation. The salesman from Great Lakes Chemical, who said tested, proven, safe, was not lying in the sense of a deliberate falsehood. He was speaking from within a system that had defined safe too narrowly, that had tested for the wrong outcome, that had measured only whether a flame went out and not whether something else was beginning. The flame went out. The foam passed. The chemicals that saved the foam from burning had already begun the slow work of entering the air. The dust, the bodies of the people who trusted the standard, and the salesmen and the regulatory apparatus that had been built to protect them. The testing had been conducted by the manufacturer. The results had been shared with regulators. What had not been shared was the study in the locked cabinet, the one that showed accumulation in the liver, the one that would not be made public until the damage was already written into the biology of a generation. The good neighbor does not need to be forgiven, because the good neighbor never admits that there is anything to forgive. The couch remains in the living room. The dust settles. The dust rises again with the morning light, stirred by a child's footsteps, invisible and patient, carrying the molecular signature of a fire that never happened. The cigarette burns in the ashtray. The blame has found its resting place. The nursery held its own climate, warm and still, the air thickened by the closed window and the radiant hum of a cathode ray television set on a low shelf. The crib mattress was new, a dense slab of foam wrapped in a waterproof cover printed with pale yellow ducklings. Beneath the carpet, a layer of rebonded polyurethane padding gave the floor a softness that made walking nearly silent. The television screen cast a flickering blue-white light across the ceiling, and in that light, every disturbance of the air became visible, a faint shimmer of suspended particles, a galaxy of ordinary household dust. The vacuum cleaner lived in the hall closet, and when it was run across the carpet, the fine material that had settled into the fibers lifted, swirled, and resettled within minutes, coating the crib rails and the plastic toys and the edges of the picture books in a film no thicker than a fingerprint. No one thought to test that dust for anything except lead. No one knew it contained a chemical signature that would be readable decades later in the blood of the child who slept in that room. 3,000 miles away, in the cold waters off the Swedish coast, the first signal was already being decoded. In 1998, a research team led by the Swedish scientist Örjan Gustafsson published a paper in the journal Nature that described something that should not have been there. Harbor seals from the Baltic Sea, animals that lived far from industrial outflows and chemical manufacturing plants, carried measurable loads of polybrominated diphenyl ethers in their blubber. The seals were not anomalies. They were sentinels. The compounds had arrived by air, carried on dust particles, and in vapor form across national boundaries, deposited into the sea by rain and snow, absorbed by plankton, concentrated up the food web into the fatty tissues of marine mammals. The concentrations were not enormous, but they were unmistakable. The flame retardants that had been designed to stay inside foam and plastic had become atmospheric travelers, and the Baltic seals were recording their arrival in the only language a body has: accumulation. PBDEs are additive chemicals, not reactive ones. They are mixed into polyurethane foam during manufacture, stirred into the liquid precursors before the foam rises and cures into a solid matrix, but they never form a covalent bond with the polymer. They remain physically dispersed, like oil droplets in a sponge. Because they are not bonded, they have no permanent address inside the material. Heat, friction, and simple diffusion over time cause the molecules to migrate out of the foam and into whatever surrounds it: the fabric covering of a couch, the air in the room, the dust settling on surfaces. A couch is not a sealed vessel. It breathes as people sit on it, as the foam compresses and rebounds, as drafts move through the living room. With every compression, a microscopic fraction of the chemical load detaches from the foam and enters the environment. The process is slow, measured in years, but it is relentless. A molecule that will not burn will also not stay put. The dust becomes the courier. Indoor dust is not an inert blanket. It is a transport medium, a suspension of skin cells, textile fibers, soil tracked in from outside, and a host of chemicals that have sloughed off household materials. Studies conducted in the late 1990s and early 2000s established that PBDEs concentrate in this dust at levels far higher than in outdoor air or soil. The chemical properties that make them persistent, their low vapor pressure, their affinity for lipids, their resistance to degradation, also make them stick to the organic matter in dust particles. A toddler crawling across a living room floor inhales the dust, licks it from fingers and toys, ingests it as part of the daily hand-to-mouth behavior that defines early childhood. Researchers eventually calculated that dust ingestion accounts for 80 to 90% of PBDE exposure in young children. The danger was not hidden in a distant factory. It was on the floor. The body that takes in these chemicals does not dispose of them quickly. Once absorbed through the intestine or the lungs, PBDEs distribute into fatty tissues where they remain for years. The half-life of beta-47, the most common congener found in human serum, is roughly 2 to 3 years. Half-life is a clinical term that masks a profound reality. It means that if a child acquires a certain body burden at age 2, half of that load will still be present when she starts kindergarten. A quarter of it will be there when she learns to read. An eighth of it when she turns 10. The exposure is not a single dose, but a continuous one, replenished every day by the dust in the home and the furniture that still sheds its invisible cargo. The developing organ systems of a child, the brain, The thyroid axis, the reproductive tissues, are calibrated to microgram-level hormonal signals. A persistent chemical that interferes with those signals does not need to be present in dramatic quantities to shift developmental trajectories. It only needs to be present during the right window. And the windows of early childhood are wide and frequently spaced. What made the Swedish data so disquieting, beyond the seals, was what the same researchers found when they turned their instruments toward human tissue. PBDE levels in breast milk samples from Swedish women had been doubling every 5 years since the 1970s. The trend line was steep, exponential, and showed no sign of leveling off. Breast milk is a fatty fluid, a repository for lipophilic compounds that the body has stored and is now mobilizing to feed an infant. A nursing mother transfers not only nutrients and antibodies, but also a portion of her lifetime chemical inventory. The concentrations in milk were a mirror of the concentrations in dust, in furniture, in air, and the mirror showed a steady rise. The researchers in Stockholm could not say what this meant for the infants who drank that milk. The epidemiological tools to answer that question did not yet exist or had not yet been applied. But the graph itself was a statement. The chemicals were moving through the food web, through the atmosphere, into the most protected spaces, into the fluid designed to nurture new life, and the direction was upward. The paradox sat quietly inside this arrangement. The flame retardant had been inserted into foam to pass a 12-second open flame test, a test that asked one thing: will this material catch fire and sustain combustion? The chemical answered that question successfully enough that regulators, manufacturers, and consumers all considered the matter settled. But the same molecule that extinguished a laboratory flame had a second life, a kinetic existence outside the test chamber in the ordinary physics of the home. It migrated out of furniture, clung to airborne particles, found its way into the lungs and digestive tracts of small children, and once inside, refused to leave. The test had measured fire resistance over 12 seconds. The residence time in a human body was measured in years. The inventors of the flammability standard had never been asked to consider whether the solution might create a different kind of burn, one that happened too slowly to see. A nursery in the late 1990s was a landscape of these objects. The crib mattress, treated with flame-retardant foam, met federal and state flammability standards. The carpet padding, often made from recycled polyurethane scrap that already contained a cocktail of older flame retardants, added its own contribution. The television, a cathode ray tube set, heavy as a small engine block, contained PBDEs in its plastic housing and circuit boards, added to prevent electrical fires. The nursing chair in the corner, the changing pad, the foam-filled toys, each item had been designed, in some small way, to resist combustion. Collectively, they created an invisible reservoir that discharged its contents continuously. The vacuum cleaner redistributed the dust rather than removing it. The air purifier, if it existed, filtered out large particles, but not the vapor phase molecules. The infant, sleeping 16 hours a day in this room, accumulated exposure during the exact period of maximum neurological vulnerability. The instruments that allowed scientists to see this problem were mass spectrometers, machines that separate and identify chemical compounds by their molecular weight and fragmentation patterns. A sample of household dust, run through a gas chromatograph coupled to a mass spectrometer, produced a distinct chromatogram, peaks corresponding to beta 47, beta 99, beta 100, beta 153, and a dozen other congeners each. eluting at a precise time, each representing a different arrangement of bromine atoms on the diphenyl ether backbone. The pattern was so consistent across households that it became a chemical fingerprint of modern American indoor life. A dust sample from Stockholm, from Boston, from Austin, from London all told the same story. The furniture had leaked. The house was not a sealed box, but a permeable membrane, and the chemicals had diffused through it. What could a parent do with this information? The question was rhetorical. The answer was nothing. The dust could not be eliminated by cleaning alone, because the source was the furniture itself, and the furniture could not be replaced with untreated alternatives because the standard required treatment. The chemicals were already in the carpet, in the walls, in the ventilation system, in the very structure of the home. A mother who read the scientific papers, who understood the implications for her child's development, could vacuum more often, could wash hands with greater vigilance, could open windows and run fans, but these measures were palliatives, not solutions. The system of fire safety had been designed without a method for recalling its chemical consequences from the indoor environments where people lived. The half-life calculation contained an unsettling property. Even if all production stopped that year, the existing body burden in the population would decline only gradually over decades. The furniture that had already been sold would continue to off-gas. The dust would continue to accumulate. The food web would continue to recirculate, and infants born in the year 2000 would carry the chemicals of the 1970s forward into their own adulthoods and into the bodies of their own children. The flame retardants had achieved a kind of generational persistence that no one had intended and no regulation had anticipated. The test flame had gone out in 12 seconds. The chemical had been given a lifetime residence visa in the human population. The Swedish breast milk data, published in peer-reviewed journals and presented at international conferences, did not cause an immediate regulatory panic. It caused a slow, grudging awareness, a series of closed-door meetings between industry scientists and government toxicologists, a proliferation of review panels and risk assessments. The chemical industry pointed out that the absolute concentrations were low, parts per billion, not parts per million, and that no human epidemiological studies had yet demonstrated a clear causal link between PBDE exposure and specific disease outcomes. The absence of evidence was treated as evidence of absence, a logic that the public health community had seen before with lead, with tobacco, with asbestos. The mothers who read the news articles, who saw the graphs of rising contamination, who looked at their own infants with a new and uncomfortable kind of knowledge, had no standing in the risk assessment process. Their bodies, and their children's bodies, had become data points in an argument about acceptable uncertainty. The nursery at night was a quiet place, the breathing of the child, the only sound besides the distant hum of the refrigerator. The dust had settled again, a fine layer on the windowsill, on the plastic cover of the monitor, on the pages of the board book stacked in the corner. A streetlight outside threw a pale orange parallelogram on the wall. The child slept on a mattress that had been tested against a flame and pronounced safe. The air she breathed, the toys she would put in her mouth in the morning, the milk she would drink before breakfast, all of it carried the chemical signature of a safety decision made decades before she was born. The fire had been prevented. The residue remained. The dust woke first, stirred by the furnace kicking on, drifting through the beams of morning light like an archive of everything the house had ever held. The fluorescent lights of the delivery room did not buzz. They hummed at a frequency just below notice, a steady 60-cycle note that had presided over 1 million births. The vinyl floor was the color of clouded seawater, scuffed by the wheels of gurneys and bassinets, cleaned after every shift with a disinfectant that left its own faint chemical signature in the air. The bassinet itself was a clear plastic tub fitted with a foam mattress, 3 inches thick, wrapped in a fitted sheet printed with pastel footprints. The mattress was not merely foam. It was treated polyurethane, impregnated with a mixture of brominated compounds that had been stirred into the polymer at the factory years before, at a concentration of 15% by weight, to ensure that if a flame ever touched it, the flame would die. The nurse who entered the room at 2:14 a.m. on that October night in 2002 was not thinking about the foam. She was thinking about the mother, whose labor had been long, and about the infant, who had arrived with a full head of dark hair and a cry that filled the room. The nurse clamped the umbilical cord in 2 places, cut between the clamps, and drew a sample of cord blood into a collection tube. The tube was labeled with a code number, not a name. It was placed in a refrigerated container with dozens of other tubes, all bound for a laboratory at the New York State Department of Health, where a scientist named David Carpenter and his colleagues were compiling a chemical census of the newborn. The study would later report its findings with a clinical precision that made the numbers no less startling. Polybrominated diphenyl ethers were present in every sample, not in 90%, not in most, but in every single one. The compounds had crossed the placental barrier, passed from maternal circulation into the fetal compartment, and settled into the blood of infants who had not yet taken their first breath of the air outside the delivery room. The exposure was not beginning in the nursery with the treated mattress and the carpet padding and the television in the corner. It was beginning before birth. The protection, if that is what it was, had begun before birth as well. The mechanism of the crossing was passive, almost indifferent. PBDE molecules are lipophilic. They dissolve more readily in fat than in water. The human placenta, a dense network of membranes and vessels designed to gatekeep between mother and fetus, is rich in lipids. The molecules partitioned into those lipids and continued their migration, following a concentration gradient, obeying the second law of thermodynamics with a kind of chemical patience. No active transport was required, no receptor needed to recognize them. They were small enough, and fat-loving enough, and persistent enough that the barrier simply accommodated their passage. It was not a breach in the fortress wall. It was a crowd moving through an open gate that had never been told to close. In the animal laboratories of the previous decade, researchers had already begun to map what happened after the chemicals arrived. The studies were methodical, iterative, conducted in rooms that smelled of bedding and feed pellets, and the faint sweet odor of laboratory rodents. Rats were dosed with PBDEs during critical windows of gestation and early postnatal life, windows that corresponded, in their compressed developmental timeline, to the 3rd trimester and infancy of a human. The doses were low, carefully calibrated, meant to mirror the concentrations that were already accumulating in American women. And then the researchers waited and watched and tested. The rat pups exposed to PBDEs were born looking normal. They nursed normally. They grew at a rate indistinguishable from their unexposed littermates. But when they were placed in water mazes, asked to remember the location of a hidden platform, they swam in confused circles. When they were startled by a sound, they took longer to calm down. Their scores on tests of learning and memory fell below those of the controls, and the deficits did not disappear with age. The chemicals had done their work quietly during the weeks when neurons were migrating to their correct positions, when synapses were forming and pruning, when the architecture of the brain was being drawn in the scaffold of thyroid hormone. Thyroid hormone is the metronome of fetal brain development. It regulates the timing of cell division, migration, and differentiation. Disrupt it, even subtly, and the metronome skips a beat. The brain builds itself slightly out of time, a gyre misplaced, a connection delayed, a pruning window missed. PBDEs, by their molecular structure, resemble thyroid hormones closely enough to confuse the receptors. They bind to transthyretin, the transport protein that carries thyroid hormone through the blood and into the developing brain. They occupy the seat without making the journey. The hormone circulates, but less of it reaches its destination. The infant brain, assembling itself in the dark, follows a blueprint that has been softly smudged. The Berkeley study that brought this mechanism into the human domain was published in 2003 in a journal called Environmental Health Perspectives, and it was written in the same measured language that scientists use when the data is stronger than they expected. The researchers had collected cord blood from a cohort of mothers in the San Francisco Bay Area, followed the children through their first year of life, and assessed their development using the Bayley Scales of Infant Development, a standardized test of mental and motor function. They had controlled for maternal IQ, for socioeconomic status, for birth weight, for breastfeeding, for the home environment. They had looked for confounders, the way an accountant looks for double entries. When the results came back, the association held. Children with higher concentrations of PBDEs in their cord blood scored lower on the Mental Development Index. The difference was not enormous, a few points on average, enough to shift a child from the middle of the distribution to the lower third. But the direction was consistent, and the dose-response relationship was linear. The more PBDEs in the cord blood, the lower the score. The chemicals were not a theoretical risk, not a laboratory curiosity, not an animal model that might or might not translate. They were measurably, statistically, associated with a dimming of potential in the first year of human life. The fluorescent lights in the delivery room did not care. The vinyl floor did not care. The bassinet, with its treated foam mattress, did not care. The mattress had been manufactured to meet a standard called Technical Bulletin 117, which had been written in California in 1975, after a high-rise fire at a furniture mart killed 14 people, and the state decided to act. The standard required that upholstered furniture pass an open flame test. A small flame applied to the foam for 12 seconds. If the foam caught fire and continued burning, it failed. If it self-extinguished, it passed. The standard said nothing about what happened to the foam when there was no flame. It said nothing about what the chemicals in the foam would do over years of slow migration, through air and dust and skin, into the bodies of the people who lived with it. It said nothing about the cord blood of infants. The chemical that had been added to furniture to protect children from burns was now in the cord blood of every newborn studied. The protection had begun before birth, so had the exposure. The two arrivals were simultaneous, indistinguishable, woven together in the same biological moment. There was no way to separate them. No filter fine enough to let the safety through and hold the damage back. They traveled together, the flame retardant and its consequences, as if they had been packaged in the same dose. The laboratory that processed the cord blood samples used a mass spectrometer, an instrument that measures the weight of molecules with an accuracy that borders on philosophical precision. The vials were uncapped under a fume hood. The blood was extracted with organic solvents, passed through a column of silica gel, and injected into a stream of heated gas. The molecules ionized, broke apart, and flew down a flight tube, where their mass-to-charge ratios were recorded as peaks on a chromatogram. The peaks appeared at predictable positions: beta 47, beta 99, beta 100, beta 153, each one a congener, a bromine atom more or less, a slightly different shape. Each one previously mixed into the polymer of a couch, a mattress, a television housing, a carpet pad, each one now in the blood of a child. What was not visible on the chromatogram was the regulatory history that had allowed these molecules to enter the supply chain without ever being tested for developmental neurotoxicity. The Toxic Substances Control Act, passed in 1976, grandfathered in thousands of existing chemicals and required no safety data for new ones unless the Environmental Protection Agency could demonstrate an unreasonable risk, a burden of proof that fell on the regulator, not the manufacturer. The foam in the bassinet had passed its flame test. The chemicals in the foam had passed through no developmental test at all. They were assumed innocent. The infant was assumed resilient. The standard was assumed adequate. The assumptions had never been audited. The rats in the earlier studies had no such assumptions. They were dosed, observed, and sacrificed. Their brains dissected and sectioned, their thyroid glands weighed, their behavior recorded in minutes and seconds and errors. The data they produced was published in toxicology journals, presented at conferences, filed in dissertation archives. It was not hidden. It was simply not acted upon. The chemicals continued to be manufactured, mixed into foam, shipped to furniture factories, and sold to families, while the evidence accumulated in the literature like sediment in a lake bed. By the time the Berkeley study found the association in human infants, the exposure had already been underway for nearly 3 decades. The delivery room in 2002 was not unique. The same scene played out in hospitals across North America, in cities and suburbs, in teaching hospitals and community clinics. The bassinet foam came from the same supply chains, met the same standard, contained the same chemical mixture. The cord blood samples, when they were tested, would tell the same story. The variation was only in degree, some infants higher, some lower, depending on the age and composition of their mother's furniture, the ventilation of their homes, the invisible geography of household dust. But none had zero. There was no zero. There was only a baseline that rose with every passing year. The nurse who had drawn the sample that October night had finished her shift, charted the birth, and gone home to her own couch, a plush sectional purchased in 1997, the foam inside still shedding its brominated cargo into the air. She did not know the chemical name of what she was breathing. She did not know that her own body and the bodies of her own children were accumulating the same compounds she had just measured in a stranger's newborn. The knowledge existed, but it was distributed in discrete pockets: a lab in Albany, a journal in Stockholm, a filing cabinet in an industry archive in West Lafayette, Indiana. The pieces had not yet been assembled into a narrative that could reach the fluorescent light of a delivery room, the vinyl floor, the bassinet. When the Berkeley study was published, it was covered in a few newspapers, discussed on a few radio programs, cited in a few policy briefs. The parents of the children in the study received their individual results in letters that were drafted with care, explaining the limitations of the data, the uncertainty of the implications, the absence of any clinical intervention that could remove the chemicals from their children's bodies. There was no antidote. There was only the knowledge that the exposure had occurred and the hope that the developing brain would find a way to compensate for the metronome that had been ever so slightly misaligned. The flame test, in its 12-second chamber, had asked a narrow question: will this foam sustain a fire? It had received a narrow answer: no, it will not. The question it had not asked, will this foam sustain a chemical legacy that reaches into the womb, was never on the form. The form was a single page, typed with a box for pass and a box for fail. The box for pass had been checked decade after decade, while the molecules migrated out of the foam and into the dust and into the blood and into the cord and into the developing brain, silent as a metronome in an empty room. The hospital bassinet in 2002, with its treated foam mattress and its pastel sheet, was a site of two arrivals. One arrival was celebrated with lights and voices and a name written on a bracelet. The other was recorded only as a peek on a chromatogram, filed in a laboratory database, and published years later in a scientific journal. The two arrivals were simultaneous. They could not be separated. The infant who slept on that mattress would carry the chemical signature of the mattress in her blood for years after the bassinet was wheeled away, and the cord stump fell off, and the first birthday candles were lit. She would grow and learn and develop, and the chemicals would remain, slowly declining, never quite gone, an archive she had never consented to keep. The study controlled for maternal IQ, socioeconomic status, and nutritional factors. The association held no government agency had required these chemicals to be tested for developmental neurotoxicity before they were put into furniture. The chemicals had been added to protect children from a 12-second flame. They had ended up inside the children themselves. The protection had a body, and the body was the child. The turnout gear hangs in the bay like a shed exoskeleton suspended from a steel rack bolted to the ceiling. It still carries the smell of the last call, a sharp wet cocktail of charred wood, spalled concrete, and melted synthetic fabrics. The helmet visors are scratched with a fine gray bloom that won't rub off. Later, a chemist would name that bloom. It is the thermal signature of polybrominated diphenyl ethers, aerosolized and condensed on every surface the smoke touched. In Oakland in 2005, the crew of Station 18 does not yet know the word. They only know that after a structure fire, the soot feels different from how it felt a decade ago, heavier, greasier, more persistent, and that the station's industrial washing machines are no longer enough to get the turnout liners clean. The California Department of Public Health had a question that year: what exactly was in that soot and where did it go? The department recruited firefighters from around the Bay Area, career crews, not volunteers, men and women who had run into living rooms, offices, and apartment buildings while the furniture was still outgassing. The study was simple in design: draw blood, note the career history, and send the samples to a laboratory that could measure the concentration of flame-retardant chemicals. The expectation was modest. PBDEs had already been detected in house dust and breast milk and the cord blood of newborns. A firefighter sees more fire than anyone. It made sense to check. What the laboratory found was a body burden that exceeded the general population's by a factor that made the researchers stop and recalculate. The firefighters' blood carried PBDE congeners at levels 2 to 3 times higher than the background, and the difference was not random. It tracked with the number of structure fires each person had worked. The more burning rooms a firefighter had entered, the higher the concentration of the chemical that was supposed to make those rooms safer. The correlation was dose-dependent, linear, and unmistakable. The mechanism behind those numbers is a property that no furniture tag ever disclosed. When polyurethane foam treated with PBDEs catches fire, the flame does not destroy the flame retardant. Heat volatilizes the brominated molecules before the foam can fully combust, releasing them into the smoke plume in aerosolized form, tiny liquid droplets and solid particles that ride the thermal column and spread through the structure. A firefighter working inside the building inhales not only carbon monoxide, hydrogen cyanide, benzene, and formaldehyde, but also the intact chemical that was injected into the couch to stop the couch from burning. The same molecule that looks inert and stable on a laboratory bench becomes a passenger in the smoke, traveling deep into the alveolar sacs of the people who depend on it for their professional survival. The bromine atoms that interrupt the combustion chain reaction in the gas phase, the very property that earned PBDEs their place in furniture, also make the compounds heavy and greasy. They condense easily on cooler surfaces, which is why the soot inside a firefighter's helmet is enriched in BD47 and BD99, the same congeners that show up in household dust. The difference is the dose. A toddler crawling on a living room carpet ingests dust through hand-to-mouth contact at a steady, low rate. A firefighter working an interior attack breathes in a concentrated aerosol pulse that lasts 20 minutes, then turns around and goes back in for another 20 minutes, then does it again 3 days later, year after year. The body of a 30-year veteran is a ledger that records every incursion, and the entries are written in bromine. The blood analysis was the first entry in that ledger to be made legible. The next entries came from endocrinology. Researchers at the University of California began to notice that the same firefighters who carried elevated PBDE levels also showed altered thyroid hormone profiles, lower free thyroxine, elevated thyroid-stimulating hormone, the hallmark of a thyroid gland that is being asked to work harder against a chemical signal it cannot interpret. The thyroid axis is the body's thermostat. A small disruption can ripple into metabolic regulation, cardiac output, and cognitive sharpness. In parallel studies, the blood of highly exposed firefighters showed elevated markers of oxidative stress, malondialdehyde, 8-isoprostane, compounds that signal cellular membranes are being damaged faster than the body's repair systems can manage. The chemical that was designed to defeat a 12-second flame was now waging a slow interior campaign against the endocrine and cardiovascular resilience of the people who run toward the fire. None of this was unique to firefighters. The thyroid disruption observed in the firehouse studies echoed what animal toxicologists had been reporting for a decade. The oxidative stress markers mirrored what pediatric researchers were starting to find in cohorts of children with high prenatal PBDE exposure. The difference was the path of entry. For most Americans, the path ran from the couch to the dust to the hand to the mouth, a domesticating exposure, invisible as fabric wear. For the firefighter, the path ran through the smoke of the burning room itself, a concentrated occupational dose that arrived on the back of a line of duty. The flame retardant did not choose one path over the other. It simply followed the laws of physical chemistry: volatilize, disperse, condense, accumulate. And yet the strangest finding of the Bay Area study was not the elevation in firefighters. It was the baseline against which that elevation was measured. The control population, the people, the researchers recruited as a comparison, the ones who had never worn turnout gear or crawled through a smoke-filled corridor, already had PBDEs in their blood at levels that would have been alarming a generation earlier. The general population had become its own control group, and the control group was already positive. The chemicals were so widespread that the researchers had to search for a population with truly low exposure, and the only group they could find were immigrants who had arrived in the United States only recently, whose bodies had been built in environments where furniture was not chemically treated. For everyone else, the American interior had already deposited its chemical signature. Then the data turned a corner that no one had anticipated. When the scientists stratified the general population samples by age, the highest PBDE concentrations were not in adults who had accumulated decades of exposure. They were in children under the age of 5. The same group that spends the most hours on the floor, the most hours with their hands on upholstered surfaces and their mouths on their hands, the same group whose developing brains were demonstrably sensitive to thyroidal disruption. Those were the bodies that carried the heaviest chemical load. The firefighters who ran into burning buildings were breathing an occupational hazard. The toddlers who had never seen a structure fire were living in one at a slower pace, day after day, in their own homes. What does it mean for a fire station to contain this knowledge? In 2005, the year of the study, the furniture inside Station 18's living quarters was itself treated with PBDEs. The couches where the crew sat between calls, the mattresses where they slept through the night, the foam padding beneath the vinyl upholstery of the station chairs, all of it shed the same chemical into the indoor dust. After a call, the firefighters would return, shower, change into clean clothes, and sit on a couch that was quietly emitting the same molecular species they had just inhaled in concentrated form on the fire ground. The station was a double reservoir. The turnout gear stored in the bay carried the legacy of past fires. The living quarters stored the legacy of the California furniture standard. The body moved between the two, and the blood kept the receipts. The story does not end in the firehouse. It circulates back into the homes the firefighters were trying to protect. The same month, the Bay Area study was being peer-reviewed. A separate group of researchers published an analysis of breast milk from nursing mothers in the Midwest, showing that PBDE levels had continued to climb even as the phase-out was being negotiated. The milk of a nursing mother in 2005 contained a chemical portrait of the furniture she had bought 10 years earlier, the television she had watched as a teenager, the carpet padding in the apartment she shared in college. That milk was fed to an infant whose thyroid gland was still calibrating the metabolic set point for the rest of its life. The firefighter's blood, the toddler's blood, the infant's milk, they were different compartments of the same slow physiology, a single system of distribution that the flame retardant navigated without effort. The flame test that started this story measured whether a piece of foam could survive a small open flame for 12 seconds. It did not measure what happened when that foam, after decades in a living room, was consumed in a real fire with real smoke and real human lungs on the other side of the air. It did not measure what happened when the flame retardant, having done its job of delaying ignition long enough for the occupants to escape, then turned around and entered the bodies of the people who arrived to finish the job. The test was a pass-fail exam on a bench. The world was the uncontrolled experiment, and the firefighter was the subject who had never been enrolled. In the bay of Station 18, the gear hangs still. The rack drips moisture from the last wash cycle into a shallow concrete trough. The diesel exhaust from the engine mingles with the faint acetic tang of drying turnout fabric. A firefighter sits on the station couch, unaware that his own blood will become one of the data points in a study that changes how California writes its fire code. He will learn the results years later, long after the standard has been revised, long after the furniture in the station has been replaced, long after the chemicals in his body have begun their slow half-life decline of 2.9 years for the most abundant congener. The decline is real, but it will never reach zero. The archive does not forgive. It only fades slowly, incompletely, and on its own chemical time. The filing cabinet was the color of old oatmeal, a 4-drawer government surplus model that had been pushed into a corner of a basement storage room in a building that no longer belonged to the company it was built for. The lock had been drilled out years ago by someone who had either lost the key or never been given one. When the drawer slid open on its dry rollers, it made a sound like a cough from another room. Inside, the manila folders had lost their original beige to a slow oxidation, turning the color of weak tea. Their labels were typed in Courier, the letters pressed deep into the paper by a machine that was now worth less than its weight in scrap metal. The first tab read simply, "Toxicity Studies, Confidential." The archives of denial are not built to last. They are built to be forgotten. They accumulate in leased storage units, in the basements of corporate headquarters that have since been sold, in the personal garages of retired scientists who signed non-disclosure agreements that outlived their careers. What they contain is not a conspiracy exactly. A conspiracy requires whispered meetings and shadowy intent. What the archives contain is something more ordinary and, in its own way, more ruinous. The record of decisions made in well-lit conference rooms by people who believed they were acting responsibly, who had convinced themselves that the question of harm was a matter of threshold rather than principle, and who had calculated that the present benefits of their product outweighed whatever costs might arrive later, somewhere else, in someone else's body. The first memo in the file was dated March 17, 1983. It had been circulated among senior scientists at Great Lakes Chemical Corporation, the West Lafayette firm that controlled the majority of the world's bromine-based flame retardant market. The subject line was printed in all capital letters, preliminary, environmental fate assessment, brominated diphenyl ethers. The language was technical, careful, and unmistakable in its implications. PBDEs, the memo noted, possessed a molecular structure that was highly resistant to environmental degradation. They were lipophilic, a term that meant they would concentrate in fatty tissue rather than being excreted. The author, a toxicologist whose name had since been redacted from the public versions of these documents, wrote that there was reason to believe that these compounds could build up in the environment and in biological systems over extended periods. Then, because even an internal memo must maintain the decorum of corporate science, he added a single sentence that would take 2 decades to escape the filing cabinet. This accumulation may cause concern if human exposure pathways are confirmed. This was 1983. The chemicals had been in commercial use for less than a decade. The Furniture Mart fire was still a recent memory in California, and the state's flammability standard, Technical Bulletin 117, was not yet 10 years old. The foam in the nation's couches was still fresh, still shedding its first dust, still beginning the slow migration from polymer to atmosphere, to lung to blood to breast milk. And already the scientists who had invented the chemical solution to fire knew that the solution was also a problem whose shape they could see but whose scale they did not yet know. The strange part was not that they saw it. The strange part was what they did next, which was nothing or less than nothing. They filed the memo, closed the drawer, and continued manufacturing the product at full capacity. To understand what happened in 1985, It is necessary to understand the architecture of chemical regulation in the United States during that period. The Toxic Substances Control Act, or TSCA, had been passed in 1976, and it gave the Environmental Protection Agency the authority to require testing and impose restrictions on chemicals that posed an unreasonable risk to human health or the environment. It was, on paper, a powerful piece of legislation. In practice, it was a sieve. The law grandfathered in approximately 62,000 chemicals that were already in commerce, exempting them from any requirement to demonstrate safety before they entered the market. For a new chemical, a manufacturer was required to submit a pre-manufacture notice, but that notice did not have to include toxicity data. The burden of proof fell entirely on the EPA. If the agency wanted to restrict a chemical, it had to prove that the chemical was dangerous, and it had to do so with data that the manufacturer was not required to provide. The chemical was innocent until the government could prove it guilty, and the government had neither the budget, the staff, nor the statutory tools to conduct prosecutions at scale. PBDEs were not a new chemical in 1985. They had been in use since the early 1970s. They were, in the language of TSCA, an existing chemical, which meant that the EPA could not even begin to consider regulating them without first conducting a lengthy and resource-intensive risk assessment. When the agency initiated a preliminary review that year, industry representatives were invited to provide input. They arrived at the meetings with binders of data, most of it generated by their own laboratories. The data showed that PBDEs were effective flame retardants. The data showed that the levels of PBDEs detected in environmental samples were low. The data did not show the internal memos from 1983. The data did not show the accumulation in liver tissue that the company's own scientists had observed in laboratory animals. The data showed what it had been designed to show, that the chemicals worked, and that there was no immediate crisis that required regulatory intervention. The EPA closed its review in late 1985 without imposing any restrictions. In the internal memorandum that summarized the decision, an agency scientist wrote that the available data were insufficient to determine the potential for adverse effects, which was technically true and practically catastrophic. The data were insufficient because no one had generated sufficient data. The data were insufficient because the system had been designed to make data sufficient only after harm had been demonstrated, which, for a chemical that accumulated in human bodies over decades, meant after the harm was already done. The record shows a risk assessment. The margin shows a risk acceptance. The difference between the two is a form of accounting that the body does not recognize. The file drawer contained another folder, thicker than the rest, whose tab read, Subchronic Oral. Toxicity Study, DE 71 inches, Rats, November 1990. D71 was the commercial name for the mixture of tetraminus, pentaminus, and hexabrominated diphenyl ethers that Great Lakes sold as its primary furniture flame retardant. The study had been commissioned by the company itself and conducted at a contract toxicology laboratory whose name had been obscured by a black marker on the document, but whose methods were standard industry practice. Rats were divided into groups and fed PBDEs at various doses for 90 days. At the end of the exposure period, the animals were sacrificed and their tissues examined. The results were unambiguous. The livers of the exposed rats were enlarged, in some cases by more than 40%. Their thyroid follicles showed cellular changes consistent with hormonal disruption. The highest dose group exhibited significant reductions in serum thyroxine, the primary thyroid hormone, at levels that would, in a human infant, be considered clinically relevant. The study's conclusion, written in the cautious language of industrial toxicology, noted that these effects were treatment-related and recommended further investigation into the mechanism of thyroid disruption. It did not recommend notifying regulators. It did not recommend suspending production. It did not recommend conducting the kinds of developmental neurotoxicity studies that would later reveal what happens to the brain of a fetus when its mother's thyroid hormones are disrupted by a chemical that has been migrating out of her furniture for years. The study was stamped confidential, proprietary business information and filed in the cabinet. It stayed there for 15 years. When a group of investigative journalists and public health researchers finally obtained these documents in the mid-2000s through a combination of freedom of information requests and litigation discovery, the industry's response was consistent and disciplined. Rat studies, the representatives argued, were not predictive of human health effects. The doses used in the studies were far higher than any human would encounter in daily life. The liver enzyme induction observed in the animals was an adaptive response, not a toxic effect. The thyroid changes were reversible. There was, in short, no proof of harm, only evidence that had been generated by the industry's own scientists, filed in the industry's own cabinets, and never shared with the regulators who might have used it to protect the public. This is the architecture of denial in its most durable form. It is not a conspiracy of silence. It is a bureaucracy of delay. Every study that remains unpublished is a study that cannot be cited in a regulatory proceeding. Every analysis that remains confidential is an analysis that cannot inform a risk assessment. Every internal memo that raises a concern and then disappears into a filing cabinet is a conversation that the public never hears. The denial is not active. It is structural. It is built into the design of a system that allows the manufacturer to control the evidence and then argues that the evidence is insufficient to justify action because the manufacturer has ensured that it will be. The filing cabinet held one more set of documents that even the most cynical observers found remarkable. Beginning in the early 1990s, the Research and Development Division of Great Lakes Chemical had initiated a program to develop what it called next-generation flame retardants. The internal project briefs described the goal in language that was remarkably candid about the fate of the current generation. The new compounds, the briefs explained, should be less persistent in the environment and less likely to bioaccumulate than the PBDEs currently in production. They should, in other words, be designed to avoid precisely the properties that had made PBDEs such an attractive product: their stability, their durability, their refusal to break down. This was not a confession. It was not written as an acknowledgement of error. It was written as a business strategy. The scientists in the research division had read the same environmental chemistry literature that the Swedish researchers would later publish in Nature. They knew that PBDEs were showing up in remote ecosystems. They knew that the levels in human breast milk were doubling every 5 years. They knew that the regulatory pressure that had ended the era of PCBs was likely to arrive, eventually, for PBDEs. And so they prepared. They began the long, expensive, scientifically demanding work of inventing a replacement, a molecule that would still stop a flame but would not stay in the body, a compound that would still satisfy Technical Bulletin 117 but would not appear in the cord blood of every infant born in the United States. They knew the ban was coming. They began preparing for it at least a decade before the first public hearing, The first newspaper investigation, the first parent who asked why her child's mattress contained a neurotoxicant. The laboratory was already working on the answer before the question had been asked in public. The paradox at the center of this archive is not that the industry acted with malice. It is that the industry acted with knowledge, knowledge that it generated itself, knowledge that it understood, knowledge that it filed away, and continued to generate while the couches accumulated in living rooms and the dust accumulated in bodies. The 1990 rat study demonstrated that PBDEs caused effects in mammals at doses that were not infinitely far from human exposure levels. The 1983 memo warned that the chemicals would persist in the environment and accumulate in living tissue. The 1985 EPA review failed because the agency lacked the data that the manufacturer possessed but did not share. At every point in this sequence, the people involved were competent professionals, doing their jobs, following the procedures that their institutions had established. The toxicity of the system was not located in any individual decision. It was distributed across the whole apparatus, the law that exempted existing chemicals, the standard that required flame resistance without requiring toxicological evaluation, the corporate confidentiality that shielded data from public scrutiny, the regulatory agency that lacked the resources to demand what it did not know it needed. What survives of this apparatus is physical. The documents in the filing cabinet are real. They have mass and weight, and the specific chemical odor of aging paper. In an abandoned office park outside West Lafayette, in a storage facility whose climate control failed years ago, the manila folders are still there, their contents slowly yellowing, the ink fading, the paper buckling in the Indiana humidity. Scientists who worked in those buildings are now retired or dead. The non-disclosure agreements they signed have expired, but the habits of discretion they learned have not. Some of them, when asked, will still not discuss what they knew and when they knew it. Others will talk, but only after assuring themselves that the conversation is off the record, that their names will not appear, that the company they once worked for will not find out. The fact of a ban is not the same as the fact of accountability. The chemicals have been phased out, but the records of their development remain locked, literally and figuratively, in a system that was designed to protect proprietary information above public health. The retention turn is this. The same filing cabinet held the budget authorizations for the next generation flame retardant program, dated 1992, 11 years before the voluntary phase-out was announced. The company had already begun to move on. The replacement was already in development. The scientists who had designed PBDEs were now designing the compounds that would take their place in the global supply chain of fire safety. They knew that the first generation had accumulated in the bodies of every American. They believed that the second generation would not. They did not know because they had not yet tested, and because the system did not require them to test, what that second generation would do when it too migrated from the foam into the dust, from the dust into the air, from the air into the next infant's cord blood. The treadmill of substitution had begun before the first treadmill had even been publicly acknowledged to exist. The archive of denial contains not just the record of what was known and what was hidden. It contains the blueprint for what came next. The hearing room in Sacramento had the stillness of a place that expected to be forgotten. The polished wooden tables reflected the fluorescent light in long, mute bands. Water glasses stood at each place, untouched, the condensation forming slow rings on the coasters. The industry representatives sat in dark suits, their posture calibrated to suggest cooperation without concession. Across the aisle, Parent advocates held photographs of their children, school portraits, mostly, the kind that hang in hallways and on refrigerator doors. The children in the photographs were not visibly sick. The damage, the advocates kept saying, was invisible. It showed up in test scores, in attention spans, in the quiet, cumulative erosion of a child's potential. The bill before the committee that day would phase out 2 commercial mixtures of polybrominated diphenyl ethers, PBDE and octa-BDE, from future production in the United States. It would not remove a single molecule of flame retardant from anyone's blood. It would not recall a single couch. It passed anyway. The couch in the lobby, beige and unremarkable, was still treated with the chemicals the bill would phase out. No one had thought to replace it. The year was 2003, and by then the evidence had been building for over a decade, stacking up in the scientific literature like sediment at the bottom of a lake. Swedish scientists had found PBDEs in the blubber of Baltic seals. A team in New York had detected them in the umbilical cord blood of every infant they tested. Berkeley researchers had published data linking prenatal exposure to lower developmental scores in toddlers. The chemicals were persistent. They were bioaccumulative. They were crossing the placental barrier and concentrating in breast milk. They were, in the careful language of toxicology, developmental neurotoxicants, a term that sounds clinical but translates, in the ordinary life of a family, to a child who struggles to focus in school, who cannot remember instructions, who lives with a brain that was built in the presence of a chemical that should not have been there. The industry had known about the potential for accumulation since the early 1980s. Internal memos from 1983 had discussed the possibility that PBDEs could build up in the environment and cause concern. The memos were not made public for 20 years. The voluntary phase-out agreement, when it came, was framed as a responsible act of corporate stewardship. The sole U.S. manufacturer of PBDE and octa-BDE, Great Lakes Chemical Corporation of West Lafayette, Indiana, entered into the agreement with the Environmental Protection Agency in 2003. Production ceased in 2004. The language of the announcement was careful. It spoke of evolving science and a commitment to safety. The company's press release did not acknowledge harm. It did not apologize. It did not admit that the chemicals it had sold for 3 decades, by the ton, into the foam of virtually every upholstered piece of furniture in America had been accumulating in human bodies the entire time. The phase-out was a legal instrument, not a confession. It stopped the future without touching the past. And the past was vast. By the time the phase-out took effect, an estimated 100 million pounds of PBDEs had been sold in the United States since the mid-1970s. Those chemicals were not gone. They had been dispersed, one couch at a time, into the living rooms, bedrooms, and nurseries of the country. They had migrated out of polyurethane foam in a slow, invisible exhalation that did not require a flame or a chemical reaction, only time, friction, and the ordinary physics of household dust. A molecule of PBDE did not need permission to leave the foam. It was not chemically bonded to the polymer matrix. It was mixed in as an additive, suspended among the polyurethane strands like raisins in a cake, and over the years it simply worked its way to the surface, caught a ride on a particle of dust, and became airborne. The process was so gradual that it was undetectable without a mass spectrometer, but it was relentless. The couch manufactured in 2002, bought new from a showroom in the suburbs, was still shedding flame retardant into the air a decade later. It is still shedding now, in whatever basement or landfill or thrift store it occupies. The chemical does not care that the factory stopped making it. The phase-out, moreover, was a national decision in a global market. The agreement applied only to the United States. Production of PBDEs continued in other countries, primarily in China, for years afterward. The same molecules, or their close chemical cousins, were still being synthesized, still being mixed into foam, still being sewn into furniture sold around the world. The global reservoir of PBDEs in existing products did not shrink after 2004. It grew. Every new couch made with DecaBDE, a related mixture that was not included in the initial phase-out and remained in use for electronics and textiles, added to the total mass of brominated flame retardants in the built environment. And the chemicals in those products continued to migrate into dust and air and, eventually, into the tissues of living things. The phase-out was a border drawn on a map that molecules do not recognize. The thing that made the phase-out feel like resolution was the same thing that made it dangerous. It gave the appearance of closure. A parent reading the news in 2004 might reasonably have believed that the problem had been solved. The bad chemical was being taken off the market. The government had acted. The couch in the living room was still there, and it still contained the bad chemical, but the narrative had moved on. The human brain is good at this, at accepting a symbolic end as a real one. The industry understood this. The phase-out was not a defeat. It was a managed retreat that protected the company's reputation while the chemicals themselves remained in the bodies of the population. It was a bluff dressed in the language of responsibility. Meanwhile, the chemical that was supposed to make furniture safer against a 12-second open flame test continued its quiet work inside human beings. The half-life of the most common PBDE congener in human blood, beta-47, was known by then to be approximately 2.9 years. For the more heavily brominated congeners like BD99 and BD153, the half-life stretched to a decade or more. A compound with a half-life of 3 years does not vanish when the source is removed. It declines slowly over multiple years, and during that time it continues to circulate through the blood, to deposit in fatty tissues, to cross into breast milk, to pass from mother to child. For a woman who was pregnant in 1995 and nursed her baby on a treated foam nursing pillow, the exposure had already happened. The phase-out would not retrieve those molecules from her child's developing brain. It would only ensure that the exposure stopped growing, and even then, only for new products, not for the dust already in the carpet fibers, the air ducts, the crevices of the floorboards. The strange part was not that the phase-out happened, but that it happened so quietly. There were no large-scale recalls, no public health alerts, no systematic biomonitoring to identify the most exposed populations. The furniture industry did not offer to replace the foam in people's couches. The chemical industry did not fund a cleanup. The burden of the exposure remained with the people who had bought the furniture, slept on the mattresses, vacuumed the carpets, and trusted that the products in their homes had been tested for long-term safety. That trust had been misplaced. The open flame test had measured only whether a piece of foam would catch fire under a specific, narrow condition. It had not measured whether the chemicals that prevented that fire would migrate out of the foam and into the bodies of children. The test had been a gatekeeper, and the gatekeeper had been checking for the wrong threat. In the years after the phase-out, independent researchers began to piece together what the industry had known and when. The documents that surfaced from corporate archives, the manila folders, the photocopied memos, the confidential toxicity studies, showed a pattern that would become familiar to anyone who studies the history of industrial chemicals. The company had run the tests. The tests had shown effects on the liver, the thyroid, the developing brain. The results had been shared internally and then filed away, classified as confidential business information. When the EPA had considered regulating PBDEs in the mid-1980s, industry representatives had argued that the benefits of flame retardancy outweighed the potential environmental risks, that the exposure levels were too low to cause harm, that the rat studies were not predictive of human health. The argument worked. The EPA declined to regulate. The chemicals remained on the market for another 2 decades. What the industry had also known, and what the archives later confirmed, was that a new generation of flame retardants was already under development. The company had anticipated, long before the public did, that PBDEs would eventually be banned. The phase-out was not a crisis. It was a product transition. The replacement chemicals were waiting in the wings, their patents filed, their toxicological profiles even less studied than the ones they would replace. The phase-out, in this light, was not the end of a problem. It was the beginning of a substitution cycle that would repeat itself in the years to come, with organophosphates and brominated phthalates and other compounds whose names would become new entries in the lexicon of indoor contamination. The industry had solved the public relations problem without solving the toxicological one. The hearing room in Sacramento emptied out. The polished tables were wiped clean. The water glasses were collected and washed. The industry representatives flew home. The parents went back to their children, their photographs tucked into folders and bags. The couch in the lobby remained where it was, its foam still slowly releasing molecules of PBDE into the still air of the State House. No one measured the dust in that room. No one tested the blood of the people who had sat there. The law had been written, and the law was good, but the law was also a document, and a document cannot enter a living room and unmake the chemistry of a couch. The problem with a persistent chemical is that it does not respect the boundary between past and present. It does not care about the date on a phase-out agreement. It does not recognize the sovereignty of a regulatory agency. It moves through the world according to its own physical properties, its molecular weight, its vapor pressure, its affinity for lipids. Those properties had been designed, deliberately, to make the molecule stable under heat. Stability under heat means stability in the environment. A molecule that will not burn will also not degrade. It will continue to exist in the landfill, in the sediment, in the dust, in the blood, long after the factory that made it has been converted to another purpose. The phase-out was a human decision made in a human institution with human language. The chemicals were not human. They had no language. They simply persisted. That persistence is the reason why, in 2020, a comprehensive analysis of global PBDE levels could estimate that the total human body burden of these compounds was approximately 1,000 metric tons. Most of that mass resided in the bodies of people living in North America, where usage had been most intensive. Every person alive during the peak years of PBDE production carried a chemical signature of the furniture they had lived with. The signature was measurable in blood and breast milk and adipose tissue. It was declining slowly among those born after the phase-out, but it was not gone. And for those born in the 1980s and 1990s, whose developing brains had been exposed in utero and during early childhood, the body burden would remain for years, metabolizing at its own slow, indifferent pace. At a fire station in Oakland, around the same time as the phase-out, researchers had found that firefighters had PBDE levels significantly higher than the general population. The flame retardants were in the smoke they inhaled, aerosolized by the heat of the very fires the chemicals were meant to slow. The firefighters had joined the ranks of the exposed, not because they sat on treated couches, but because they ran toward the flames. The chemical that was supposed to protect them had become an additional hazard. The irony was precise and cruel. The open flame test had not prevented this outcome. It had ensured it. The phase out, then, was not a conclusion. It was a hinge. It swung open a door that led from one chemical era to another, from couches treated with PBDEs to couches treated with Firemaster 550 and other proprietary mixtures whose safety had been assumed rather than demonstrated. The new chemicals would soon be found in household dust at levels comparable to the old ones. Some of them would prove to be neurotoxic, others endocrine disrupting. The treadmill had not stopped. It had only changed speed. The dust in the living room does not know that the standard changed. It does not know that the factory in El Dorado stopped receiving PBDE shipments. It does not know that the hearing in Sacramento ever took place. The dust simply accumulates, particle by particle, on the television screen, on the windowsill, on the floor where the toddler plays. It contains the legacy of the old couch, the old television, the old carpet padding. It contains the molecular memory of a fire safety decision made in 1975, before most of the people living in that house were born. The phase-out was an act of law. The dust is an act of chemistry, and chemistry has the longer memory. The children in the photographs are grown now. They are adults with their own homes and their own furniture. The chemicals from their childhood couches are still in their blood, detectable with the right instrument, a quiet archive of the years before the ban. The ban gave them something the previous generation did not have: the assurance that no new PBDEs would be added to the furniture they buy today. But it did not give them a way to remove what had already been deposited. The body does not have a detoxification pathway for brominated diphenyl ethers. It can only wait and metabolize, and slowly, over decades, clear the compounds through the liver and into the waste stream. But even then, the chemicals do not go away. They enter the sewage, the sludge, the soil. They continue their journey through the environment, moving from one compartment to another, from foam to dust to blood to milk to child to soil to water to sediment to the bottom of a lake, where they will remain for centuries, a geological signature of the flame retardant era, long after the fire that was supposed to justify them has been forgotten. The living room in 2008 smells like a promise. The new couch, sectional, upholstered in a microfiber the color of wet slate, dominates the room, still releasing the faint acrid sweetness of fresh polyurethane foam. On the back of one cushion, a white fabric tag sewn in. At the factory carries the block-lettered legend, Meets, California, Technical Bulletin, 117, Requirements. The words are printed in the same bureaucratic typeface that has governed American furniture for 3 decades, but the chemical language beneath them has changed. The old brominated molecules, the ones that accumulated in blubber and breast milk and umbilical cord blood, are gone. In their place is a mixture of compounds that almost no independent scientist has studied. The dust that settles on the television screen already contains them. The replacement was not a secret. It arrived with a brand name, a safety data sheet, and the full confidence of the corporation that manufactured it. Great Lakes Chemical Corporation had become Chemtura in 2005, a corporate rebranding that coincided neatly with the voluntary phase-out of PBDE and PBDE. The company had seen the regulatory pressure building for years, had watched the Swedish breast milk studies make their slow way from academic journals to newspaper headlines, had read its own internal toxicology memos with a clarity that the public never possessed. The phase-out was presented as responsible stewardship, a voluntary agreement with the Environmental Protection Agency, proof that the industry could regulate itself without heavy-handed government mandates. But behind the press releases, the company's chemists had been working on a replacement since the early 1990s. The product they eventually brought to market was called Firemaster 550. The name was a deliberate echo. Firemaster had been the trade name for the old PBDE mixtures, Firemaster 550 for the pentabrominated formulation, Firemaster 836 for the octa. The number changed, but the lineage remained visible. Firemaster 550 was not a single chemical but a proprietary blend, and its exact composition was initially guarded as confidential business information. Over time, researchers pieced together the recipe, a mixture of brominated phthalates, triphenyl phosphate, and a suite of other organophosphate compounds. The bromine atom still provided the flame-quenching mechanism, interrupting the combustion chain reaction in the gas phase, just as they had in the old chemistry. The phthalate backbone was new, so were the phosphates. The combination was supposed to be less persistent, less bioaccumulative, less likely to travel from the couch to the dust to the body. The problem was that almost no one outside the company had tested whether that was true. The Toxic Substances Control Act, the federal law that had governed industrial chemicals in the United States since 1976, did not require manufacturers to generate new safety data before bringing a replacement chemical to market. If the company had not submitted the toxicity studies to the Environmental Protection Agency, the EPA had no obligation to review them. If the compound had never been studied by independent academic laboratories, there were no independent results to review. Firemaster 550 entered the stream of American commerce in the same regulatory vacuum that had welcomed its predecessor. The burden of proof lay not on the manufacturer to demonstrate safety, but on the public to demonstrate harm after exposure had already occurred. After the chemical had already migrated into household dust, after the metabolic machinery of millions of bodies had already begun to process the unfamiliar molecules. The dust was the first witness. Environmental chemists who had spent the 1990s and early 2000s cataloging PBDE levels in indoor dust began, after the phase-out, to detect rising concentrations of entirely different flame-retardant compounds. They belonged to a broad chemical class called organophosphate esters, or OPEs. Tris-1,3-dichloro-2-propylphosphate, often abbreviated as TDCPP, appeared. So did triphenyl phosphate, or TPP, one of the components of Firemaster 550. So did a dozen other related compounds, some of them already in use as plasticizers and hydraulic fluids, others newly deployed as flame retardants. By 2012, a meta-analysis of dust samples from homes across the United States had identified more than 40 distinct flame-retardant chemicals in household dust. The replacement for penta-BDE was not a single safer molecule. It was an entire chemical class, introduced into the indoor environment without systematic toxicological screening. The dust clung to furniture, to television screens, to the small hands of toddlers who crawled across carpeted floors and put their fingers in their mouths. The exposure pathway that had made PBDEs a pediatric health concern, ingestion of contaminated household dust, remained wide open. The chemicals that entered the body through that pathway were different in structure, but they entered the same tissues, circulated in the same blood, crossed the same placental barrier. The question was not whether exposure was occurring. The dust studies made that clear. The question was what the new chemicals would do once they arrived. The early answers came from laboratory animals and cell cultures, the same screening tools that had flagged PBDEs as developmental neurotoxicants years before the human epidemiology caught up. Organophosphate flame retardants, it turned out, were not biologically inert. TDCPP, one of the most widely detected OPEs in household dust, was found to be neurotoxic in cell models, disrupting the same neuronal differentiation pathways that PBDEs had targeted. Triphenyl phosphate interfered with hormone signaling. Several OPEs were associated with reduced sperm quality in epidemiological studies of adult men. The pattern was not identical to the PBDE story, but it was uncomfortably familiar. A chemical added to consumer products in the name of safety was displaying biological activity that no one had asked it to demonstrate. Then came the wait. In 2011, a research team led by scientists at the University of North Carolina published a study that no one in the flame retardant industry had commissioned. They exposed pregnant rats to Firemaster 550 at doses designed to reflect the levels found in household dust, not extreme toxicological doses, but chronic, ambient, ordinary exposures of the kind that a human infant might absorb from crawling on a treated carpet. The exposed pups were born healthy. They nursed, they grew, and then, quietly, their bodies began to diverge from the controls. The female offspring of the exposed mothers gained significantly more weight than the control animals, even though both groups ate the same laboratory diet and lived in the same cages. The difference was not subtle. The exposed rats became obese, and the obesity persisted into adulthood. Their metabolism had been recalibrated in utero, their energy regulation altered at a fundamental level. The researchers examined fat tissue, liver function, and gene expression, and they found changes consistent with metabolic disruption, altered insulin signaling, altered lipid metabolism, the quiet reprogramming of a body that had been taught, before birth, to store more energy than it needed. The flame retardant was not just present in the tissues, it was changing the instructions. The study did not prove that Firemaster 550 caused obesity in humans. No single rat study can prove a human health effect, but the finding was not an outlier. Other organophosphate flame retardants were subsequently shown to interfere with metabolic function in animal models and in cell lines. The class of chemicals that had replaced the developmental neurotoxicants appeared, at least in part, to be metabolic disruptors. The replacement for a chemical that altered brain development was a chemical that altered the body's relationship with energy. The industry had solved a public relations problem. The headline, "Flame retardants found in breast milk," had been retired, without solving the underlying toxicological one. The new molecules were not inert. They were simply mysterious in a different way. The couch in the 2008 living room did not carry a label explaining any of this. The tag said what the law required it to say, that the furniture complied with California Technical Bulletin 117. That standard, as it existed in 2008, still required the open flame test. The foam inside the couch still had to survive 12 seconds of direct flame without igniting. The chemical industry had met the requirement with a new mixture, and the mixture had passed the same test that the old one passed. The test chamber smelled the same, the flame extinguished, the foam charred. The checklist was complete. But the standard was measuring the wrong thing. The 12-second open flame test was a proxy for fire safety that did not correspond to the way furniture actually caught fire in homes. Smoldering cigarettes, not open flames, were the leading cause of upholstered furniture fires. The test had never measured the chemical burden of the treated foam. It had never asked what the chemicals would do after the couch left the factory, after the dust began to accumulate, after the toddler began to crawl. The test was a closed loop, a flame, a piece of foam, a pass or fail. The chemical industry had mastered the loop. The loop asked nothing about metabolism. The replacement treadmill had begun to turn. As one flame retardant was phased out under public pressure, another arrived to take its place, often with even less toxicological information available at the time of market introduction. The cycle was not accidental. It was a structural feature of a regulatory system that allowed chemicals to be sold first and studied later, that treated each compound as innocent until proven guilty in a court of science that could take decades to convene. The laboratory notebooks of academic toxicologists filled with data on new flame retardants, but the data always lagged behind the market. By the time a chemical's effects were understood well enough to justify regulation, its manufacturer had often moved on to the next generation. The patent portfolio turned over. The brand names changed. The dust continued to settle. The atmospheric marker for this era was not the acrid test chamber of the 1970s, nor the factory dust of El Dorado, but the quiet domestic accumulation of a suburban evening. A flat-screen television on a particle board stand, its back panel warm with the heat of electronics. A child's plastic toy bin in the corner, the plastic itself potentially treated with flame retardants that migrated from the polymer matrix into the air. A vacuum cleaner run on Saturday morning, its exhaust stirring the fine particulate matter that had settled on the carpet fibers. The dust rose, swirled, and resettled, and with it rose the molecules of the replacement chemicals, entering the respiratory tract, settling on food preparation surfaces, finding their way into the bodies of everyone who breathed the indoor air. The human body, when exposed to a foreign organic molecule, does not simply ignore it. The liver attempts to metabolize the compound, to attach a hydroxyl group or a glucuronide moiety that will make it more water-soluble, easier to excrete. But some of these metabolic products are more biologically active than the parent compound. The liver's detoxification machinery can inadvertently create a new molecule with new properties, a transformation product that the original manufacturer never tested. The organophosphate flame retardants, with their phosphate ester bonds, are susceptible to enzymatic hydrolysis and oxidation, and the resulting metabolites can circulate in the blood for hours or days, interacting with receptors whose normal ligands are hormones, neurotransmitters, or metabolic signals. The body is not a passive container for the chemical. It is an active chemical processing plant, and the products of that processing are as unregulated as the original compounds. In the years after the phase-out, the concentrations of PBDEs in human blood began, very slowly, to decline. The decline was a public health success, the result of advocacy, journalism, scientific persistence, and regulatory pressure. But the decline was not an ending. As the brominated flame retardants fell, the organophosphate flame retardants rose. The total flame retardant burden in household dust did not decrease. It shifted in composition. The bodies of Americans born after 2005 carried a different chemical signature than their parents, but they did not carry less chemical. They carried a new archive. The furniture industry had, by this time, begun to explore alternatives that did not require additive chemicals at all. Barrier fabrics, inherently flame-resistant fibers, and design changes that reduced the availability of fuel for smoldering cigarettes were all technically feasible, and some manufacturers were quietly adopting them. But the chemical pathway remained the dominant compliance strategy. The supply chains were established. The cost was low. The regulatory infrastructure was built around chemical solutions. The test chamber still expected foam that would not ignite. The paradox of the replacement era was that it exposed a deeper flaw in the logic of chemical fire safety. Flame retardants were not a solution to a fire problem. They were a solution to a test problem. The test was a material performance standard that did not reflect real-world fire scenarios, and it created a captive market for whatever chemicals could pass it. Each generation of flame retardants was slightly different in structure, but the fundamental transaction was the same. Add a foreign molecule to the indoor environment, document that it passed a 12-second flame test, and defer indefinitely the question of what else it did. The replacement cycle was not a failure of regulation. It was regulation working exactly as designed, slowly, reactively, one chemical at a time, while the inventory of untested compounds grew faster than the capacity to study them. The dust on the television screen in 2008 contained a chemical that had not existed in any home a decade earlier. It had been synthesized in a pilot plant, formulated into a viscous amber liquid, mixed into polyurethane foam at a concentration of 10 to 15% by weight, and shipped to a furniture factory where a worker had poured it into a mold. The worker had worn gloves and a respirator as required by the material safety data sheet. The consumer who sat on the finished couch wore no protective equipment. The exposure was not an accident. It was the intended consequence of a regulatory standard that had asked a narrow question and received a narrow answer. The retention turn is not a dramatic revelation. It is a quiet expansion of scale. The replacement was not one chemical but an entire class. By 2012, the dust in the average American home contained a chemical cocktail of flame retardants whose combined effects had never been studied. The treadmill was not a temporary transition between a bad chemical and a good one. It was the permanent architecture of a system in which safety was defined by a flame measured in seconds and blind to everything that happened after the flame went out. The couch was new. The tag was compliant. The dust was settling. And somewhere in the liver of a child who had never seen a fire, a metabolite of a compound called triphenyl phosphate was quietly binding to a receptor that had evolved to recognize something else entirely. The body does not know the difference between a flame retardant and a hormone. It only knows the shape of a molecule and what that shape unlocks. Chapter 10: The Reckoning with the Standard. The test chamber still stands in a state laboratory in Sacramento. It is not a grand room. It is a steel box, roughly the size of a hotel closet, lined with ceramic wool and instrumented with thermocouples that measure heat in degrees Fahrenheit and seconds. In the old days, a technician would place a block of polyurethane foam on a stand inside the box, light a Bunsen burner, and hold the flame against the foam for 12 seconds. A stopwatch counted the interval. If the foam continued to burn after the flame was removed, it failed. If it self-extinguished, it passed. The test was called the open flame test, and for 38 years, it governed what could and could not sit in an American living room. The strange part was not that the test existed. It was that for nearly 4 decades, no one seriously asked whether a 12-second open flame was the right fire to fear. The test had been born in the aftermath of a tragedy, the 1975 Los Angeles Furniture Mart fire, an inferno that climbed through 14 stories of upholstered showroom displays, killing 14 people and injuring dozens more. The state's response, Technical Bulletin 117, was written in the language of emergency. It demanded that filling materials resist a direct flame. It did not ask what kind of fire most often started inside a home. It did not ask what would happen to the chemicals required to meet that resistance once they migrated out of the furniture and into the air. The test was a memorial to the 14 dead, etched in regulation. A memorial cannot ask questions. By 2012, the research had become impossible to ignore. Study after study, conducted not by activists, but by fire safety engineers, showed that the primary ignition source for residential furniture fires in the United States was not an open flame. It was a smoldering cigarette. The numbers were stark. Cigarettes caused roughly 88% of upholstered furniture fires that led to death in the home. Candles, matches, lighters, space heaters, all the open flames that the test imagined, accounted for a fraction. The cigarette, abandoned in an ashtray or dropped between cushions, did not produce a tall, bright fire. It burned without flame, a dull orange crescent that ate into the fabric 1 millimeter at a time, releasing heat and smoke long before any ignition occurred. A piece of foam that passed the 12-second open flame test with chemical bravado could sit silent and indifferent while a cigarette smoldered against it, then ignite hours later from the accumulated heat. The test was testing for the wrong fire. It had been testing for the wrong fire since the day the ink dried on the original bulletin. This knowledge was not new in 2012. Fire scientists had been publishing on the cigarette ignition problem since the late 1970s. The cigarette industry had funded some of the research, hoping to prove that the couch, not the cigarette, was the danger. What emerged from their studies was a perverse confirmation. The couch was indeed dangerous, but only because the couch had been engineered to resist a flame that rarely appeared, using chemicals that did not address the actual threat. A smoldering cigarette does not care how much bromine is in the foam. It heats the material slowly to the temperature of decomposition, releasing flammable gases that can ignite without any open flame present. The chemical that interrupts the gas phase combustion chain reaction cannot stop the solid phase smolder. The flame retardants, in other words, were solving a theoretical problem at the expense of an actual one. They were like a boat designed to survive a tidal wave that sank in every rainstorm. The movement to revise TB 117 began in the California legislature with a bill that was, by Sacramento standards, modest. It simply directed the Bureau of Home Furnishings and Thermal Insulation to evaluate whether the open flame test could be replaced with a test that reflected real-world fire scenarios. The chemical industry did not meet it with modesty. The trade association that represented flame retardant manufacturers, the North American Flame Retardant Alliance, argued that removing the open flame test would endanger lives. They brought to the hearings a prop, a small sofa treated with flame retardants, which they set alight with a blowtorch. The sofa did not burn. The demonstration was intended to prove that the chemicals saved lives. It proved, instead, that blowtorches are not common household objects. It proved that the industry had built a multi-billion-dollar business on answering a threat that existed more vividly in the test chamber than in the home. The legislators sat behind a dais of polished wood, their water glasses sweating rings onto the agenda sheets. One of them, a Democrat from San Francisco who had read the epidemiological literature, asked a question that no one in the room could answer cleanly. How many lives have the flame retardants saved, and how many have they harmed? The industry representative, dark suit, calm voice, the practiced patience of a man who had answered versions of this question since the 1980s, replied that no one could quantify the lives saved because prevention is invisible. He was correct. Prevention is invisible, but so are the chemicals in the blood of a newborn. The record shows a life. The margin shows a cost that no one had been required to measure. The revised standard, TB 117-2013, was finalized in November of that year and went into effect on January 1, 2014. It did not ban flame retardants. It simply changed the test. The new test used a lit cigarette, a standardized smoking machine that drew air through the tobacco, producing a slow, even smolder placed directly on the fabric of a mock-up seat cushion. The foam was still present, but now the question was whether the assembly would ignite from a cigarette, not whether the naked foam would resist an open flame. Most upholstered furniture could pass this test without any added flame retardant chemicals at all. Dense, tightly woven fabrics like cotton duck or wool could smother the cigarette before it transferred enough heat to the foam. Polyester batting or a thin barrier layer of inherently flame-resistant fiber could do the same. The chemical pathway that had filled American couches with bromine for 40 years was no longer the only option. It was not even the easiest option. The market, freed from a regulatory requirement that had never been scientifically justified, began to shift. Manufacturers announced new lines of furniture free of added flame retardants. Their press releases spoke of naturally fire-resistant materials and consumer choice, as if these had been impossible before. In truth, they had only been impossible under a rule that equated safety with chemical infusion. If you walked into a furniture showroom in late 2014, you would have seen the new compliance tags hanging from the armrests of couches, a white rectangle with black type reading TB 117-2013 in place of the old TB 117. Salespeople, trained on talking points that the industry had distributed, explained that the couch no longer contained added flame retardants. They said this with relief, as if the couch had been cured of something. Some customers, holding the tag between thumb and forefinger, would ask whether it was safe to sleep on a couch without flame retardants. The salesperson would say yes. The tag would say it was compliant. The dust on the showroom floor, tracked in from the parking lot and the streets, would say nothing at all. The reckoning with the standard did not happen in the test chamber, or in the legislature, or in the showroom. It happened in the gap between what the regulation required and what the regulation understood. The original TB 117 had been written by fire safety engineers working in the aftermath of a catastrophe. Their expertise was contained and kinetic. They knew how fire moved through a building, how foam burned, how a 12-second exposure could cascade into a room-sized blaze. They did not know, were not trained to know, were not funded to know, how a brominated compound moved through the human body, how it concentrated in fatty tissues, how it crossed the placenta, how it disrupted the delicate thyroid signaling that guides the construction of a fetal brain. The regulation was a fire code. It became a public health intervention without anyone intending it to be. The state had mandated a chemical exposure for every resident of California, and by extension for most of the country. to answer a fire scenario that occurred in only a small fraction of actual fires. The cost had been borne silently, inside cells, across generations. The moral architecture of the story is uncomfortable because it lacks a villain simple enough to satisfy. The chemical industry did not invent the open flame test. The state did, in good faith, believing it was protecting citizens. The state did not understand the toxicology of PBDEs when it wrote the standard. The science was still emerging, and the industry that possessed the emerging science chose not to share it. The scientists who ran the rodent studies in the 1980s and 1990s published their findings in specialist journals that regulators rarely read. The furniture manufacturers, caught between a fire standard and a price point, purchased the cheapest foam that passed the test, which happened to be foam filled with bromine. The consumer sat on the couch and brushed the dust from the cushions and never asked what made the foam inside resist a flame. The chain of responsibility was too long for any single link to feel the weight of the whole. The system produced an outcome that no one had chosen, but that everyone had enabled. The danger was not hidden in the poison. It was hidden in the division of labor. The new standard did not recall the old furniture. There was no mechanism for recall. The couches manufactured in 1995, 2002, 2011, the ones with the PBDE-laden foam and the old compliance tag, remained in living rooms, dens, and nurseries across the country. Their foam continued to shed microgram quantities of brominated compounds into the dust that settled on coffee tables and hardwood floors and the synthetic fibers of carpet padding. A hand-me-down crib mattress, stored in a basement for a decade, still contained the chemicals that had been added before the ban. When a family placed that mattress in a nursery for a second child, the exposure resumed. The half-life of the most common congener, beta-47, is roughly 3 years in the human body, but the furniture does not care about half-lives. It releases its inventory steadily, indifferent to the calendar. The standard changed. The dust did not. In the years following the revision, the market for flame retardants did not collapse. It simply pivoted. Some manufacturers began using different chemicals, organophosphates, chlorinated tris, proprietary mixtures whose toxicological profiles were even less studied than the PBDEs they replaced. The treadmill that had started in the 1970s continued to turn, one chemical stepping forward as another stepped back, the test chamber always demanding some solution, the body always receiving some residue. The true reckoning would require not just changing a test, but asking why the test existed in the first place, and why the burden of fire safety had been placed on the molecules inside the furniture rather than on the ignition sources that started the fires. That question was larger than any legislative hearing. It involved the cigarette industry, which had fought fire-safe cigarette laws for decades while championing flame-retardant furniture as the responsible alternative. It involved building codes, electrical standards, the economics of rental housing, the installation of smoke detectors. It involved the peculiar American habit of solving systemic problems by inserting chemicals into objects and then forgetting the chemicals were there. A furniture showroom in 2014, the fluorescent lighting soft on the display couches, the salesperson folding a compliance tag under a cushion so that it won't scratch the customer's arm, the customer lowering herself onto the seat of a sofa and pressing her palm into the armrest, feeling the give of the foam. She does not know the name of the man who wrote the original bulletin in 1975. She does not know the chemical structure of pentabromidiphenyl ether. She knows that the couch feels comfortable and that the tag says it meets a fire standard. She knows that her children will sit on this couch and do their homework and fall asleep watching television. She knows, in the way that all of us know without quite believing, that safety is a promise made by people she has never met, on terms she will never read, in a room she will never enter. She buys the couch. The dust in her home will be waiting for it when it arrives. The centrifuge in the Seattle lab had been running for 27 minutes when the technician removed the rack of specimens and began the transfer to the mass spectrometer. It was 2:15 a.m. on a Tuesday in February 2020, and the building was silent, except for the whir of pumps and the faint clicking of the autosampler. The samples had been drawn that morning from 37 women enrolled in a long-term birth cohort study, all born between 1980 and 1990, all living within 50 miles of the city. The technician loaded the vials, checked the calibration standards, and started the run. The instrument is not a storyteller. It produces chromatograms, jagged lines on a screen, peaks rising at specific retention times that correspond to specific molecular weights. A trained eye can read those peaks like a signature. At 4.7 minutes, a sharp peak corresponding to a mass-to-charge ratio of 485.7, the most abundant isotope of a molecule with 4 bromine atoms arranged around a diphenyl ether backbone, known in the literature as BD47. At 6.1 minutes, a broader peak for the pentabrominated congener beta-99. At 8.2 minutes, a smaller but unmistakable peak for BD153 with its 6 bromine atoms. The chromatogram on the screen was from a 35-year-old woman born in 1985. It could have been from any of them. The pattern was as consistent as a fingerprint pressed into 100 different pages. What the machine was reading was the chemical residue of a couch. More precisely, it was reading the residue of a couch, a television, a crib mattress, the carpet padding in a childhood bedroom, the foam in the rear seat of a minivan. The woman had never worked in a factory that made polyurethane foam. She had never opened a barrel of flame-retardant concentrate. She had simply lived in an American house between 1985 and 2004, and the dust in that house had entered her body through her mouth and her lungs and her skin, and once it was inside, it had stayed. The serum half-life of BDE 47 inches human blood is approximately 2.9 years. That means that if a person were exposed to a single dose today, half of those molecules would still be circulating in her bloodstream in the autumn of 2025. For BD99, the half-life is closer to 5 years. For BD153, the most heavily brominated of the common congeners, the estimate ranges from 7 to 12 years depending on body fat composition and metabolic rate. These are not poisons that the liver flushes in a matter of days. They are persistent guests. They settle into the lipid-rich tissues, adipose, brain, breast, and they take years to check out. A woman exposed to peak PBDE concentrations in the mid-1990s, during childhood, would have been eliminating those chemicals for most of her adult life and still showing detectable levels at age 35. The math is simple enough to be unsettling. A 12-year half-life against a 35-year lifespan means the original deposit is not gone. It is merely halved. The cohort study that produced the blood sample was not looking for proof of exposure. That proof had been established decades earlier, when Swedish researchers first found PBDEs in the breast milk of nursing mothers and watched the concentrations double every 5 years. What this study was looking for was the biological legacy of an exposure that began before birth. The women in the cohort had all been pregnant at least once. Their children, now adolescents, had been enrolled at delivery, and their cord blood frozen, and their finger stick samples collected at intervals ever since. The pattern was clear enough that the statisticians stopped being surprised by it. The PBDE levels in the children's blood tracked the levels in their mother's blood at delivery. The exposure had crossed the placenta. The children had been born with a chemical dowry that they had not earned, would not remember, and could not spend. The mechanism is not mysterious. PBDEs are lipophilic and resistant to metabolism. They cross the placental barrier passively, drawn by the same lipid gradients that move nutrients from mother to fetus. Once in the fetal circulation, they distribute to the developing brain, the liver, the nascent fat deposits. The infant then drinks breast milk, which concentrates the same compounds. The exposure continues through toddlerhood, when hand-to-mouth contact with household dust adds a second loading dose. By the time the child enters school, the body burden is already declining, slowly, logarithmically, but the critical windows of brain development have closed. The question of what those chemicals did during those windows is the question that keeps an entire subfield of environmental epidemiology awake at night. The numbers that answer that question are not small. A landmark 2020 meta-analysis calculated the total PBDE body burden of the global human population at roughly 1,000 metric tons. To put that figure in proportion, the entire amount of penta-BDE ever produced for the North American market was approximately 100,000 metric tons. 1% of the total product, give or take a loading error, ended up inside human beings. The rest is still in the environment, in landfills, in soil, in lake sediment, in the blubber of Arctic seals, but the fraction that migrated from couch foam into dust and then into bodies is not trivial. Most of that human inventory resides in the tissues of people living in the United States and Canada, where the regulatory standards were most aggressive and the use of flame-retardant foam was most widespread. The body of a middle-aged American in 2020 carries, on average, a PBDE concentration that is 5 to 10 times higher than that of a European of the same age. The difference is not genetic, it is architectural. It is the difference between a couch made in North Carolina in 1996 and a couch made in Stuttgart. What is strange about the body burden is that it is not a permanent condition exactly, but it is not a temporary one either. The residence time is so long that it behaves like a generational transfer. The chemicals rise in the population, peak, and begin a slow decline only after the source is removed. In this case, after the voluntary phase-out of penta-BDE and octa-BDE in 2004. But the decline is not a clearance, it is a dilution. As people age, they add new body mass, their metabolic rate slows, and the PBDEs stored in their fat are gradually released, metabolized, and excreted. The concentration in their blood drops. In a perfectly sealed system, the total mass of PBDEs in a human body would decrease by half every 3 to 12 years. In a perfect system, the chemicals would eventually vanish. But human bodies are not sealed systems. They die. And when they die, the chemicals do not disappear with them. They are buried. The nearest municipal cemetery to the Seattle lab is a sprawling park of grass and headstones 3 miles north of downtown. The soil there is a loamy glacial till, well drained, with a pH that hovers around neutral. It is an environment designed to decompose a body in 20 to 30 years, leaving only the skeleton and the surgical hardware. The PBDEs in the fat of a decedent do not decompose. The brominated diphenyl ether structure is stable against microbial degradation, hydrolysis, and photolysis. It will survive the decay of the casket, the collapse of the vault, the slow percolation of rainwater through the grave soil. It will join the groundwater on a timescale measured in centuries, not decades. In 100 years, the chromatogram from a sample of the soil beneath that cemetery will still show the same peaks at 4.7 and 6.1 and 8.2 minutes. The archive will have moved from blood to earth, but it will not have closed. In 2019, a doctoral student at the University of Michigan took a sediment core from the bottom of Lake Huron and sliced it into half-centimeter intervals. She extracted the lipids, ran them through a gas chromatograph, and plotted the PBDE concentrations against the year of deposition, which she determined from the depth and the known sedimentation rate. The plot showed a barely perceptible trace in the layer corresponding to 1970, a steep upward curve through the 1980s and 1990s, a sharp peak in 2005, and a gradual decline after 2008. The shape of the curve was a near-perfect echo of the annual production volumes of Great Lakes Chemical Corporation, whose plant had been located only 250 miles to the south, in Indiana. The chemicals had left the factory, entered the furniture, entered the dust, entered the air, fallen onto the surface of the lake, and settled into the mud. The lake bottom was now a geological reference library for the flame retardant era. The bodies are another such library, but they are a library that is slowly closing. The chemicals are declining in the living year by year, as the cohort born after the phase-out grows up in homes with less treated furniture. A child born in 2015 has a blood PBDE level that is, on average, 40% lower than that of a child born in 2000. The trend is real. The phase-out worked, in the narrow sense that the loading of new material into the human population has slowed. But the legacy population, the 300 million Americans who lived through the peak years, will carry their stores for the rest of their lives. Their bodies are a respiratory ledger. Every molecule still present represents a molecule that has not yet been exhaled, not yet metabolized, not yet deposited into a landfill or a cemetery plot or a lake bed. The half-lives are running. The arithmetic of elimination is grinding forward. But the chemicals are not gone. They are only moving from one archive to another, from the warm archive of the living to the cold archive of the soil. In the Seattle lab, the mass spectrometer finished its run at 5:40 a.m. The technician reviewed the chromatograms, logged the results, and saved the batch file to the secure server. The peaks were exactly what she expected. The woman born in 1985 had a beta-47 concentration of 32 nanograms per gram of lipid, which placed her in the 75th percentile for her age group. The technician did not know the woman's name or her address. She did not know what kind of couch the woman's parents had bought when she was a toddler, or whether the foam inside it had been manufactured at the El Dorado plant in 1986, or whether the dust in her childhood bedroom had been vacuumed weekly or monthly or not at all. She only knew the peaks. She noted the file number, shut down the instrument, and left the lab just as the winter dawn was beginning to lighten the windows. The chemicals had been counted. The archive was up to date. The sum of all those peaks, across all those samples, across all those years, was slowly, inexorably, heading into the ground. The rain begins without ceremony. It falls on the black plastic bags, on the crushed armrests and exposed springs, on the foam padding that was once a couch in a living room in a house that someone called safe. The foam is yellow now, brittle where the sun has found it, dark where water has pooled in the folds. It has been here since 2004, when the family replaced the furniture with something newer, something that still smelled of the factory. The old couch came here, to a landfill outside of Gary, Indiana, and it has been quietly dissolving ever since. Not dissolving. That is the wrong word. Dissolving would imply that the material is breaking down, returning to simpler components, rejoining the soil. The polyurethane foam is fragmenting, crumbling into smaller and smaller pieces under the mechanical stress of weight and weather, but its chemical structure remains largely intact. And the flame retardant, the PBDE mixture that was mixed into the foam at a factory in El Dorado, Arkansas in 1992, is not fragmenting at all. The molecules are whole. The bromine atoms are still bonded to the diphenyl ether rings. The chemical that was designed to resist fire is now resisting everything else: sunlight, water, the slow metabolism of soil bacteria, the passage of decades. This is the architecture of residue. It is not a building, though it has rooms. It is not a monument, though it will outlast most monuments. It is the accumulated material consequence of a decision made in a hearing room in Sacramento in 1975, propagated through supply chains and factories and furniture showrooms, and now deposited in the geological record of the continent. The couch in the landfill is not an isolated object. It is one node in a distributed archive that extends from the foam in the waste pile to the dust in the attic to the sediment at the bottom of Lake Michigan. The chemicals are moving. They have always been moving. The question is where they stop. The strange part is not that the chemicals persist. The chemists who designed them understood that halogenated aromatic compounds are stable. That is why they work. The strange part is that no one measured the persistence against the benefit. Or rather, someone measured it, but the measurement was filed away, and the filing cabinet was closed, and the office was locked, and the building was eventually abandoned, and the documents inside yellowed and curled and were forgotten. The flame extinguished in 12 seconds. The test chamber was cleaned, the foam passed, and the ledger was never balanced. Let me tell you about the sediment cores. In the early 2000s, researchers from the United States Geological Survey began collecting sediment samples from the bottoms of lakes across the Great Lakes region. They used a device called a piston core, a long tube that is driven into the lake bed and then withdrawn, bringing up a vertical column of mud and silt that has accumulated over decades. Each centimeter of sediment corresponds to a period of time. The top layer is the present, the layer below is the recent past, and so on down through the strata. By dating the layers and analyzing their chemical composition, the researchers could reconstruct a history of what had fallen into the lake year by year since the mid-20th century. What they found was a clear PBDE deposition pattern in the layers corresponding to the 1950s and 1960s. Before the widespread use of the chemicals, levels were barely detectable. Trace background from some diffuse source, perhaps atmospheric transport from early industrial production. In the layers from the early 1970s, the levels began to rise. The rise was slow at first, then steeper. By the 1980s, the PBDE concentration in the sediment was doubling every few years. The peak came in the mid-2000s, right around the time of the voluntary phase-out agreement. After that, the curve bent downward. It did not drop to zero. It began a slow, gradual decline that will take decades, perhaps a century, to return to anything like pre-industrial levels. The sediment at the bottom of Lake Michigan contains a geological record of the flame retardant era. The chemicals arrived not through direct discharge of factory waste, though there was some of that in certain watersheds, but primarily through the air. PBDEs are semi-volatile compounds. They evaporate slowly from the surfaces of furniture and electronics into the indoor atmosphere, and from there they migrate outdoors through open windows and ventilation systems. Once in the outdoor air, they attach to airborne particles, dust, soot, pollen, and travel. Some of those particles settle out over the Great Lakes. They land on the surface of the water. They sink. They accumulate in the sediment, layer upon layer, a chemical stratigraphy that will be readable for as long as the lake exists. What the core shows is not a crime scene. It is a receipt. Every molecule of PBDE in that sediment was put there by a decision. The decision to require the open flame test. The decision to use additive flame retardants rather than barrier fabrics. The decision to keep the toxicology studies confidential. The decision to continue production while the evidence of accumulation grew. None of those decisions were made by the people whose bodies now carry the chemicals. But the chemicals do not distinguish. They settle into the sediment the same way they settle into the adipose tissue of a child. They are impartial. They are the only part of this story that is. The rain continues to fall on the landfill. The water percolates through the layers of crushed furniture and household garbage. It picks up dissolved chemicals as it moves, not only PBDEs, but phthalates, bisphenols, organophosphates, the whole contemporary cocktail of consumer chemistry. This liquid, called leachate, collects at the bottom of the landfill and is channeled into treatment systems. The treatment systems are designed to remove pathogens and heavy metals. They are not designed to remove halogenated flame retardants. The chemicals pass through. They enter the groundwater. They travel. A couch disposed of in 2004 will still be present in the leachate from that landfill a century from now. This is not speculation, it is chemistry. The half-life of PBDEs in sediment has been estimated at more than 20 years, and under anaerobic conditions, the kind found in landfills and deep lake bottoms, the degradation rate is even slower. The molecules will outlast the plastic bags. They will outlast the landfill liner. They will outlast the regulatory framework that allowed them to be produced. And now we come to the final irony of the fireproof house. Despite 40 years of widespread use, there is no clear evidence that PBDEs reduced fire deaths in the United States. This statement is not a hypothesis or an accusation. It is the conclusion of multiple epidemiological analyses conducted after the phase-out, when enough data had accumulated to ask the question seriously. Fire fatality rates in the United States declined steadily from 1980 to 2010. The decline was substantial, from roughly 30 deaths per million population in 1980 to roughly 10 per million in 2010. But when researchers controlled for other factors, the flame retardants disappeared from the equation. The primary driver of the decline was smoke detectors. The percentage of American homes with at least one smoke alarm rose from less than 10% in the early 1970s to over 95% by the mid-1990s. Smoke detectors provide early warning. They wake people up. They give them time to escape. The effect was so large and so consistent across different populations and housing types that it alone explains most of the reduction in fire deaths. The secondary driver was the introduction of fire-safe cigarettes. Beginning in the 1980s, a series of state laws required that cigarettes be manufactured with reduced ignition propensity, cigarettes that would self-extinguish if not actively puffed. The tobacco industry, which had spent decades fighting these laws, eventually capitulated. The fire-safe cigarette became the norm, and residential fire deaths from smoldering cigarettes, the most common ignition scenario for fatal fires, dropped sharply. Other factors contributed: improved building codes, better emergency medical services, public education campaigns, the gradual decline in smoking rates. When all of these variables were entered into the statistical models, the effect of flame-retardant chemicals on fire mortality was indistinguishable from zero. The chemicals may have contributed nothing to fire safety. They may have contributed measurably to the chemical burden of every American. These two statements are not contradictory. They are adjacent facts in the same ledger, and the ledger is telling us that the cost and the benefit were never on the same page. The record shows a decline in fire deaths. The margin shows an increase in the concentration of persistent neurotoxicants in human breast milk. The two curves moved in opposite directions for 30 years. No single agency was responsible for comparing them. The agency that regulated furniture flammability did not measure chemical exposure. The agency that regulated chemicals did not measure fire deaths. The architects of the fire safety system had designed a building with no door connecting the two rooms. The fireproof house was never fireproof. It was only chemically fortified, at a cost that no one measured until the chemicals had already entered the bodies of the people inside. Walk through the house now. It is a house like any other in an American suburb. The living room has a couch manufactured in 2015, after the standard changed, after the phase-out, after the replacement cycle began. The furniture tag reads, "Meets California TB1 17-2013 requirements." The foam inside does not contain PBDEs. It may contain organophosphates. The dust on the television screen is different from the dust that would have been there a decade ago, but it is still dust, and it still contains chemicals whose toxicology is not fully known. The crib mattress in the nursery is made of natural latex. The parents bought it after reading an article about flame retardants in children's products. The window is open. The air outside is clean. The parents do not know about the sediment in Lake Michigan, or the leachate from the landfill in Gary, or the half-life of BDE 153 inches human blood. They know that the furniture is different now. That feels like enough. But the body remembers what the house forgets. The mother, born in 1987, carries PBDEs in her blood and in her breast milk. The chemicals entered her body during the peak years of use, when she was an infant crawling on treated carpet, a child sleeping on a treated mattress, a teenager doing homework on a couch manufactured under the old standard. Her exposure is declining now. The phase-out is real. The environmental levels are dropping, but the decline is slow. The half-life of the common congeners is measured in years. The daughter, born in 2018, will receive a smaller dose than her mother did, but she will still receive a dose. The placenta does not block these chemicals, neither does time. What the mother received was not a poisoning in the clinical sense. The levels in her blood are measured in parts per billion, trace quantities that do not cause acute symptoms, do not trigger alarms in a hospital lab, do not produce a recognizable syndrome. What they produce is a probability. a shift in the distribution of outcomes across a population. More children scoring slightly lower on developmental tests. More cases of ADHD. More metabolic disruption. None of it attributable to any single molecule, any single couch, any single decision. The architecture of residue is statistical. It is built from increments. It shows up not in the individual case, but in the population curve, and only when someone thinks to look. The sediment core is the most honest witness. It does not negotiate. It does not apply for regulatory approval. It does not conduct cost-benefit analyses. It simply accumulates, year after year, a physical record of what was released into the world. A future geologist, 100 years from now, will be able to date the flame-retardant era with precision. The layer corresponding to 1975 to 2004 will be visibly distinct in the chemical profile. Future historians will have to explain what motivated a civilization to saturate its domestic interiors with persistent neurotoxicants in the name of a fire scenario that accounted for less than 5% of residential fire deaths. They will have to reconstruct the logic of the test chamber, the politics of the tobacco industry, the confidentiality of the animal studies. They will have the sediment. They will have the documents. They will have the bodies. The bodies will be buried, but the chemicals will not be. PBDEs have been detected in the tissues of Arctic marine mammals, in the eggs of peregrine falcons, in the blubber of killer whales, in the breast milk of Inuit mothers who live thousands of miles from any source of industrial production. The chemicals have achieved a kind of global citizenship. They travel on wind currents and ocean currents and the slow migration of contaminated dust. They cross borders without passports. They accumulate in the fatty tissues of organisms at the top of the food chain. This is the final architecture, not the house, not the furniture, not the landfill, but the biosphere itself, chemically altered by a decision made in a single state legislature in the 20th century. The scale of the consequence is disproportionate to the scale of the cause, but that is the nature of persistent chemicals. They do not respect the boundaries we draw around our intentions. The rain stops. The landfill steams. The foam in the crushed couch continues its slow, invisible release of brominated molecules into the air and the water. The sediment in Lake Michigan settles, layer upon layer, a chronicle written in parts per trillion. The mother holds her daughter. The daughter's blood carries the signature of a couch her grandmother sat on decades before she was born. The standard changed, the furniture changed, the bodies changed, but the dust remains. The dust settles. The dust wakes first in the morning, long before the alarm, long before the smoke alarm, long before anyone remembers the fire. What the fire left was not a scar but a record. What the record shows is not a crime but a cost. What the cost teaches is still being learned. There is a truth that became visible only after the dust had been measured, the sediment cored, the blood sampled, the regulatory archive unlocked. The open flame test in the steel chamber measured whether a piece of foam would sustain combustion for 12 seconds. It did not measure what would happen when the chemicals that extinguished that flame began their slow migration from the cushion into the air, from the dust into the lungs of a toddler crawling across the living room floor, from the mother's blood across the placenta into the cord blood of a child not yet born. The test passed decade after decade, and the chemicals accumulated in bodies the way they accumulated in the sediment layers of Lake Michigan. Year after year, a rising curve that no one had been asked to approve. The yellow dust on the band saw in the El Dorado factory, the firefighters' turnout gear still carrying the soot of a burning couch, the filing cabinet in West Lafayette with the confidential liver study from 1983. These are the objects the evidence changed. They are no longer isolated facts. They belong to a single pattern. The couch that passed the test was also the couch that exhaled its chemical contents into the home. The industry that ran the safety studies also locked them away. The standard that promised protection from fire did not ask what the chemicals would do after the fire did not happen. What the story leaves with us is the distance between invention and consequence. A molecule designed to interrupt a combustion chain reaction was so stable that it interrupted the chain of trust itself. It persisted inside furniture, then inside dust, then inside the body, and then in the groundwater and the lake bed. The useful thing carried a hidden cost that was never part of the test. The test was narrow. The cost was broad. Now the pressure begins to ease. The darkness above thins, black water turning gray, light widening overhead. The archive file closes, but the evidence it holds does not disappear. It comes back with us, carried from depth, settled into understanding. If this kind of quiet descent into science and history is what you came for, you can subscribe to The Deep Archive. The dust settles. The record remains.